Thanks so much for joining us for our inaugural AI Med Paediatrics virtual conference. My name's Alexis May. I'm Director of Content for AI Med. Just a couple of housekeeping points from me before we get started. This meeting is taking place from 11 a.m. to 3 p.m. Eastern Time today and 11 a.m. to 2:30 p.m. Eastern Time tomorrow. All speaking sessions will take place here on the main stage. We encourage you warmly to use the chat function to the right of the screen, and please feel free to submit questions and comments during the day, and we'll endeavour to answer as many as we can. Just having a look through the event platform, please also check out the essential download section for additional content. At 12:40 p.m. Eastern Time today, we'll be running two roundtable networking sessions. Conversations will be gently moderated by members of our speaker faculty. You can find more details in the networking tab. Please do note that these roundtables are designed to facilitate networking. Commercial pitches will not be tolerated. If you do have any issues with the platform, please contact my colleague AJ at ai-med.io. Now, as you hopefully know, AI Med is the only clinician-led movement dedicated to artificial intelligence in health and care, connecting and educating clinicians, healthcare executives, and industry to inspire action and to drive forward the deployment of AI. To complement meetings like today, we've developed the AI Med Connect platform to facilitate communication and collaboration between the key stakeholders involved in the implementation of AI in healthcare. The simplest way to sign up for this is to search AI Med on your app store and download the app. Right, that is enough from me. Thanks again for joining us, and I'm going to hand over to Dr. Chang now to get things started properly.
Thank you, Alexis. Welcome, everybody, from Southern California. We're heading into the fall, seems like overnight, and just want to say that I really do miss seeing all of you. I feel like I know most of you. And I also want to thank the International Society of Pediatric Innovation, or ISPI, the leadership, as well as the members for joining us today. So I thought I'd spend about half an hour and just talk about reflections on 2020, especially in the context of the pandemic, and also give you an update on what's happening in artificial intelligence, including a few basic slides for those of you who are just getting to know this domain. So I think what's happened in the last decade or so is the convergence of three main forces. One is the capability of the algorithm, particularly neural networks. And then the second is the capabilities of cloud computing and storage. And lastly, the capabilities of chips, particularly with the gaming industry giving us the dividend of GPUs. So those three forces converging really has given artificial intelligence and the dawning of a new era. So I think what artificial intelligence can do right now is to take some of the aspects of the part of our brain that deals with perception. So you've seen a lot of work in the medical image interpretation area as well as integrated data analytics. It is just starting to get more seriously involved in what I call the cognition part of our brain, which is complex decision-making as well as creative problem solving. So I think the next decade or two are going to be very exciting as we head into the cognition era in artificial intelligence. And the operation part where we do manual tasks is going to be and remains to be among the more challenging areas. So I want to just pause here and thank all of the caretakers, both adult and children, in this really very, very difficult time and on the front lines of taking care of patients. So we thank you for all you do and wish you well. So speaking of the pandemic, what's happened since January is and is very relevant for artificial intelligence is if we think about the information overload, medical knowledge doubling time has been 60 days. And if you just look at the pandemic since January, as of early this morning on PubMed, there's over 70,000 manuscripts published. And that's about 1 every 6 minutes. So tremendous surge of information that sometimes is very, very hard to take in. I think another issue relevant to artificial intelligence during the pandemic is that a biophenomenon like a pandemic that involves also human behavior is often very difficult to predict. And as you know, artificial intelligence right now is about making predictions. So we've gone from something that's simple and complicated to now something complex and maybe even chaotic when you look at the pandemic, especially in certain countries. So I think part of the issue here is the limited role as of now of artificial intelligence because of the complex nature of biomedical phenomenon like the pandemic. I think another key issue and a deficiency we've known for a long time, but really, really brought to the surface is the data issue, that it's complex, incomplete, and there's lack of sharing globally. So I think as we have talked about in the past at other meetings, the foundational layer of AI is really data and information. So if those layers are not robust, then as you go up the pyramid, then knowledge and information and knowledge and intelligence really are unstable and difficult to do. I think throughout the next couple of days with our all-star faculty, we'll delve into related issues. One of them is explainability. How do we take into account the more sophisticated methodologies in artificial intelligence, like deep learning, while being able to explain this to stakeholders is a challenge, but I think it's a challenge that we can overcome. Another area that we'll address, especially with a keynote later this morning and afternoon, is regulation. How would the regulatory issues be accommodated during this surge in methodology in artificial intelligence? And especially given what's happening with the Black Lives Matter movement, as well as the Me Too movement, there's ongoing increasing debate and discussion about the ethics of artificial intelligence and bias and bringing equity into algorithms so that we don't end up automating and perpetuating biases that people may even unintentionally tend to have. So if we look at publications in artificial intelligence and pediatrics, really a lot has been happening in the last 3 to 5 years. But before then, it really has been relatively quiet. So I was part of a team that wrote a review of artificial intelligence in pediatrics. And since a couple of years ago, we've seen encouraging public signs of publications that involve subspecialties other than the ones that have been publishing more, such as radiology, cardiology, ICU, and surgery. So we're starting to see papers in infectious disease as well as other subspecialties. We're also now seeing publications on use of artificial intelligence in pediatrics in our known journals, such as Paediatrics, which hasn't been happening in the last few years. And lastly, we're also seeing more and more activity in mental health, which is a very challenging area, but happens to be one of the areas that artificial intelligence can really make a big difference in various journals. So I think increasing activity. So if you're relatively new to artificial intelligence, it's probably good to just say a few words about machine learning. So machine learning is the computers able to find patterns and make predictions based on data, and does tend to get better at making those predictions. There's basically two kinds of machine learning, supervised and unsupervised learning, and that's a relatively simplistic division. But a lot of work is being done in the area of supervised learning with classification, and you'll hear examples throughout the next 2 days. And then regression that we're all more familiar with. I think the truly exciting part of machine learning for the future will be unsupervised learning. And I'll talk about that also during this talk, because I think it's going to give us new patient subtypes and phenotypic expressions and therapies. And I think it's a vastly under-leveraged type of machine learning. Now, a lot of the excitement about artificial intelligence has been centered on something called convolutional neural network, or CNN. And you've been probably watching a lot of CNN recently, so just think of CNN and artificial intelligence as a medical image tool that's very, very powerful. It has some similarities to the way the human visual cortex looks at medical images through two main processes called convolution and pooling. And when I started back in school about a decade ago, this was not even really in existence. So that's just giving an idea how fast the AI methodologies have progressed. So this has been a big help in terms of medical image interpretation, and just been a Cambrian explosion of CNN methodologies and tools that are now available. This is a scattergram looking at the different CNNs in terms of capability, speed, and the number of parameters. So definitely we're getting better at picking the right ones for the task at hand. So a lot of exciting work with convolutional neural network. And this was one of the first landmark papers that involved human ophthalmologists, as well as the deep learning algorithm from Google. And this is basically looking at the accuracy and performance of using CNN versus human ophthalmologists. And you can see that the human ophthalmologists are in the colored dots. The black line is the algorithm that, if you look at the area under the curve, only the human ophthalmologist in purple has superseded the capability of the algorithm. But I think it's more about synergy between human and machine rather than human versus machine, as we talked about. Something that's very exciting also that's being done now is something called generative adversarial network, or GAN. And it's because in pediatrics, we don't have sometimes hundreds or thousands of patients of a given diagnosis. So something like GAN can really be useful to synthesize data so that the machines can learn. So I think we'll be hearing more about the use of GAN in pediatric medicine when we talk about artificial intelligence. For those of you who are in the ICU, anesthesia, cardiology, I think it's particularly important also to know that there's something called recurrent neural network, or RNN, and that's particularly good for time series data. So CNN is for medical images, RNN is more for time series data. So if you combine the two, you can probably do a project in moving videos, which is something that we're involved in at Children's Hospital Orange County, looking at echocardiograms and looking to collaborate also with other centers. So RNN is for time series data. So this is in the context of the COVID-19 pandemic. There's been really good work, although some of the aspects is disappointing in terms of real-time ICU information and analytics. But what's been encouraging is on the therapy side. This is an article that just came out looking at use of artificial intelligence in drug repurposing. So taking drugs that have been already approved and find a place in the therapy for COVID-19. And the grand vision is to use this artificial intelligence capability to not just repurpose drugs, but repurpose drugs on an individual basis. So essentially combining drug repurposing with precision medicine. And you'll hear more about that later in the program. So the exciting thing about artificial intelligence is totally changing the way we make diagnoses and also design therapies for the individual patient. And this article came out of Lancet Digital Health, which has been really a good source for artificial intelligence papers. On the also exciting front is the use of deep learning for predicting viral protein quaternary structure just based on the genomic sequence. So compared to the real viral proteins, the predictions have been very close, and that's immensely useful for designing new drugs for combating the virus. Other exciting developments, I'm just going to highlight these areas. One is natural language processing. It is so important right now that we actually have a separate session now focused on natural language processing, and you'll hear a module later. But what's particularly exciting using natural language processing, which is essentially a methodology to allow machines and humans to communicate verbally and in print. And now natural language processing has progressed to natural language generation and understanding, which are tougher procedures. But GPT-3, if you just remember the acronym, is a transformer type of natural language processing tool that's going to be a game changer in the area of natural language processing. So the enigmas of dealing with language in electronic records hopefully will be less of an enigma through the next few years, given the GPT-3 that's arrived and been here since July. Another, I think, underleveraged area is robotic process automation, which can be immensely helpful with repetitive tasks that machines should be able to do. As my friend Sean Lane says, it takes the robot out of humans, and I know even clinicians have plenty of examples of doing things that machines really should be doing, not just because it's faster, but it's also perhaps more accurate. So robotic process automation is making its headway into hospitals and health systems. So in essence, if we look at the time curve, in the orange is how humans think about the future, and green is how technology actually develops. We can see that we're about here. So we're still overestimating capabilities of AI, and hence some hype around the technology. But I think 10 years from now, when we do AI Med Pediatrics in 2030, we'll realize, looking back on 2020 and how we underestimated the capabilities of artificial intelligence. So I think, and that's been consistent through other technologies as well. So I think it's an exciting decade to come. I think we just need to be very patient and try to generate the future. So a little cartoon break. Oh my God, that's offensive. And you're familiar with that tool that on the computer. So as Alan Turing famously said, we can only see a short distance ahead, but we can see plenty there that needs to be done. So what can we expect in the future, now that you've heard about the present and a little bit about the past? So I think first and foremost in pediatrics, and maybe particularly in pediatrics, because we have such a heterogeneous patient population and also so few patients sometimes, we really need to put data sharing as one of the highest priorities. And as a matter of fact, the first session following my talk will be on data and data sharing. And this is a dream of a project that my former Stanford professor and colleague and friend, Tim Chow, and I were thinking of organizing. It's a pediatric cloud project. So we like to basically connect all the machines and from all the children's hospitals around the world, so that in essence, we have the biggest imaginable repository of data, and particularly image data. So I think that's a doable project. There are close to 500 children's hospitals around the world. This is actually something that can be done if only the humans can align and put their institutional agendas aside and just work together. And I think we're particularly excited about this project. I think another aspect of the future of artificial intelligence, as this pandemic has demonstrated, we really need something real-time and agile when we think of a clinical question. So this is something that our data scientist, Howard, and I wrote up about how to do agile clinical research, and involved our whole team, Doctors Terriman, Louis, and Dr. Feaster. So instead of the traditional sort of back and forth between the domain experts and data scientists when you do a project, I think it's much more productive and meaningful if we just work side by side throughout the whole process, which is something that we try to espouse as clinical projects. So I literally spent hours during the week with our data scientists and work on projects together. I maintain my data science skills, and they also get clinical input. So I think it's usually a more robust project. I think, as I mentioned earlier, I think an underutilized area that's going to be extremely powerful, and particularly pediatrics, is unsupervised learning. Very, very few manuscripts have been published on the use of unsupervised learning in pediatrics. And yet I think this is going to be one of the most robust methodologies in looking to gain insight into pediatric patients, particularly rare diseases. I think reinforcement learning in this decade will start to be a force. Reinforcement learning, just in a sentence, essentially you set up learning in such a way that the agent is going to get a reward for a favorable outcome through its actions. So this is the mechanism that was the underpinning for AlphaGo from Google and DeepMind to defeat the human champion in the game Go. I think that's only the beginning, hopefully, of many, many more advances in this particular subdomain of reinforcement learning. I think it's going to be particularly valuable if we have humans involved here to teach the tool to become better decision makers along with the humans. I think in this decade, we'll also see quite a big advance in the area of wearable technology. And how do we converge wearable technology with artificial intelligence? In something we call local analytics or local AI. So essentially, we'll start to see artificial intelligence-like tools embedded in the devices that our patients will be wearing. And I think it's going to be particularly valuable in pediatric patients. And there's also edge analytics, which is in your local computer, and then cloud analytics. So essentially, it's analogous to the developing a peripheral nervous system to the central nervous system, which is the cloud AI. So I think it's an exciting decade. We'll see lots of advances in this area as well, as wearable technology really takes off this decade. I think a truly exciting advance is going to be an area of cognitive architecture. So now that we're in the statistical period of machine and deep learning, I think we're really, really ripe for another major paradigm shift in artificial intelligence in the form of cognitive elements or architecture on top of deep learning. So I think I'm not saying the era of deep learning is over. I'm just saying to look forward to the next era, which is going to involve the cognitive architecture. And the exciting thing is that it means that the clinicians really have to help with this big advance of a era. So I believe in the power of swarm intelligence, or lots of humans having their knowledge, wisdom, experience together, and then you add the machine capabilities on top of that. I think that's going to be a tremendous increase in the capabilities of artificial intelligence. The machines can't do it by themselves. The humans, not only should they be involved, but they should be involved as a large group. So I think that's going to be the biggest advance this coming decade, is swarm intelligence and cognitive architecturing of artificial intelligence. I think another area that I'm particularly excited about and getting involved in is how do we add elements of artificial intelligence to the already quite mature area of augmented and virtual reality. So I think I call that intelligent reality, because if you bring some aspect of artificial intelligence to all the extended reality methodologies, then that's going to be a real game changer when you talk about education training in a clinical setting, particularly in pediatrics, given that we have so few patients sometimes of a given diagnosis. So in essence, we like to look at artificial intelligence as a resource, not as a black box necessarily, or as something that's mysterious that only machine learning experts can do. But let's look at artificial intelligence as a resource that you can apply to just about anywhere and any subspecialty. So it's not a panacea for sure, but I think a lot of the problems that we face now can really be partly or wholly solved with a machine-derived methodology, and it's just vastly underleveraged. So if we dream of the future vision of precision medicine and population health, that's a very tall order in terms of the knowledge gap. And so we really need to move from evidence-based medicine that we've sort of been training our doctors and nurses in, and to what I call intelligence-based medicine, which involves data from all sources to improve our capabilities as clinicians in taking care of children. So in the words of Antoine de Saint-Exupéry, if you want to build a ship, don't drum up the men and gather wood, divide the work and give orders. Instead, teach them to yearn for the vast and endless sea. I like that because I think that's how we can look at artificial intelligence when we talk about education, which is a very important part of all this. So I look at educating clinicians in the area of artificial intelligence as giving them a third perspective. So there's the artificial intelligence perspective from the data scientists, and then clinical medicine from the clinicians. But wouldn't it be wonderful if we join forces, and just like the convolution process, we have a third function basically from two domains. So that third perspective is really going to be critical, I think, this coming decade. So we also, in addition to working with data scientists, we also need to perhaps have a small cohort of clinicians actually get better educated in this area. So I think that's going to elevate the game in this area. So I've been the privileged editor of a textbook that's been out now for a few months. And quite a few of you were invited authors to write commentaries in this book. And I think one of the best things I learned from putting this book together is just how much dividend that we're going to get in the future using this amazing resource that's ahead of schedule. And there's also a journal that's been launched now called Intelligence-Based Medicine, the same name as the textbook. And I'm the privileged editor-in-chief, and I'll be reviewing my 99th manuscript this week. So it's been a very, very productive year despite the pandemic. And most papers have been co-authored or authored by clinicians. So I'm very, very proud of the clinicians that really getting into this area. And then I'm working on a video and book series. Among the book series, first volumes will be cardiology, as well as AI in medicine for healthcare leaders. We've also launched the American Board of Artificial Intelligence Medicine, or ABAIM, and we offer a 2-day review course. It's very comprehensive, basically covers the entire textbook. And then we'll be offering certification starting first quarter of next year. So it's for everybody, not just clinicians, but it's for healthcare leaders, nurses, technicians, even students. We really aim to democratize the area of artificial intelligence in healthcare. And if you're looking for continual activity, we also have a monthly meeting. We just had a meeting yesterday. We have over 200 people in our Medical Intelligence Society database. It's formalized now as a society, and it's very complementary to the AI Med meetings because you hear about journal articles, many topics. We usually have a speaker. It's a really good way to keep involved between AI Med meetings. And we meet the second Monday of each month, and we have an annual meeting in July. So please participate and support the cause of the Medical Intelligence Society. So the bottom line is the ARC is leaving. Please at least get to know this area and understand data as a very minimum to really help the transformation that this is capable of achieving. And just like the pandemic, the AI medicine and pediatric medicine, in the words of Winston Churchill, now this is not the end. It is not even the beginning of the end, but it is perhaps the end of the beginning. I think that's a very appropriate saying for the pandemic and AI in pediatric healthcare. And a special hello from my girls here in Laguna Beach to all of you around the world listening in. It's I desperately miss seeing people, but at least it's good to see you virtually. And I want to thank my generous donor, Michelle Lund of the Sharon Disney Lund Foundation, and to help me with the vision of the Medical Intelligence and Innovation Institute that focus on AI in healthcare, as well as my great friends and colleagues and mentors at Stanford School of Medicine. And there's my contact information. So please feel free to email me or even text me on my phone. My cell phone's there, and thank you very much. So with that, we are exactly on time. So want to now turn the moderator role back to Dr. Peter Lawson, who's a close friend and colleague and has always been so supportive of all the people supporting the domain of data science in bringing more certainty in clinical practice. So Peter.
Hello, Anthony. Thank you very much. It's great to see you, and hi to everybody online. That was a wonderful introduction, Anthony, and really hit the high points about this next session as well. Intelligence needs data. It's not only a resource, data is an asset, and how we manage that asset is critical if we're going to derive the value from it and do the appropriate analysis that then drives change and drives changes in behavior as well. So this next session is really looking at aspects of data at the very front end, how it's generated, managed, shared, and some of the challenges around that. We've heard that this is rapidly changing, and that's certainly the case. We have 4 wonderful speakers to look at data and its various elements, from research and digital platforms and virtual environment through radiology and imaging, cardiology and imaging, and then genomics and pharmacogenomics as well. All of these are data-intense environments, and the management of that data is critical as to the way in which it is then used as an asset to derive the changes that we need to see. I will share my screen now. I want to just set the scene a little by saying that data can come from many sources. This is just one broad cartoon of that, from the genome, transcriptome, proteome, metabolome, and there's a huge amount of information clearly in all of these areas that people are specifically looking at. How we combine this information to understand the patient's phenotype is critical. Of course, there's a huge amount of clinical data that's streaming from the EMR and from imaging sources, from natural language processing. All of that information also provides us an overall picture of the phenotype, patient, the diagnosis, how well the patient's responding to treatment. I'm sorry, I have shared it. You can't see it there now at all. I apologize. Can you see it now? Okay, thank you. So I apologize, everybody. This cartoon shows the sources of data that we can use to try and understand our individual patients from a disease perspective, as well as their response to treatment and subsequent outcomes. There's not only the biologic components to this, there's the data that's contained within imaging, NLP, the EMR, and increasingly the application of social determinants of health that we all know have a big impact. So the data sources are many. And if you look at, in fact, this is from JAMA, you can just look at the tapestry, they've called it, of potentially high value sources that can be used to link an individual for healthcare. And there's the types of data may be structured or unstructured, as Anthony was talking about, but I don't need to go through each of these particular components, but you can see once again, there's a whole lot of biologic data as well as other sources that we need to try and assimilate into the outcomes for our patients if we are to both improve the treatment we provide and, of course, most importantly, the outcomes for our patients longer term. Now, all of this is very relevant now, particularly in the United States, because to get to this data, there's an increasing need for us to share the data. And the 21st Century Cures Act is one example of this, where there is now a need for certification requirements by 2022 for there to be basically interoperability between electronic health records. And this will allow health information to be not only accessible, but exchanged and used without special effort. So they're trying to reduce the barriers, open up the access to information. Now, this is not only for the patients, of course, but also broadly across our fields. And I think that's going to be a very important act that will drive changes in the development of APIs and the way in which we can share data. More recently, in fact, the end of October, the NIH finalized their policy for data management and sharing. And that was designed to promote the management and sharing of scientific data generated from NIH-funded or conducted research. And once again, a very important statement that is essentially going to mandate us to have a platform in place when we are developing NIH-funded studies that allows that data to be accessible and shared. So there are regulatory requirements that are going to drive change here. And I think that's for the better. But the challenge with data is that we need it to be explainable, believable, actionable at the bedside. With that, we need to have it robust, replicable, and relevant. The amount and type of data is important and needs to be reliable. And as we heard from Anthony, there are concerns around that related to fragmentation. The data may be incomplete, incorrect, inconsistent. One of the problems I note in my own area around physiologic data science in critical care is definitions vary within various databases. Aligning definitions and terminology is very critical. And as noted, ability to extract that data and relate it to care processes and decisions is really important. And it really gets to the cognitive architecture that Anthony was talking about. Now, roadmaps have been put in place to try and get data, do responsible machine learning. This from Nature Medicine last year by a group of data scientists who were trying to provide a roadmap as to how the data can be collected, harmonized, represented, biases dealt with. And they actually brought out a couple of very important aspects around ethical considerations as to how the data is not only collected, but the patient populations and how it will be used, and through to deployment and making sure that that's responsibly done as well. Now, my own area in critical care is focused on the use of high-frequency time series high-frequency physiologic signals to use them for both predictive modeling of a physiologic state and the risk for an event within that state. And one of the problems that we found early on was how to manage the data, because we want to make sure the data isn't purged. We want to make sure that it's not overly curated, that it's collected in its raw form, and that it's stored permanently. To do so needed a practical solution for storing and retrieving this data, which Andrew Goodwin in my group was able to develop. And these are just a range of signals that is collected routinely from every critical care bed in the intensive care unit of sick kids, has been for the last 4 years. There's over 3.3 trillion data points on that in that database now. And they come with various symbols, various frequency as well, and being able to manage all of that variability is critical in any database. Unfortunately, there isn't an off-the-shelf system right now for doing this, so bespoke systems are being developed, but I think over time we'll see that we get a much more standardized platform to be able to collect this data, organize it and structure it in a way that then makes it usable and accessible. Because in the end, what we want in certainly the critical care environment is to be able to use the live signals and historic data to develop an end-to-end life cycle management, so that we can pre-process the data in some cases, try to avoid just a dump of data that somebody else then has to try and structure, but a structured process that then will feed to experimental models for offline training and online training, and then to online inference. And that's I think, all in this end-to-end life cycle management. But some of the challenges going forward is, what are the data sharing models? How do we make sure that the data is de-identified, and it may be centralized for analysis, or it may be a distributed format where there is local analysis and then aggregation of results. Both have merit, both depend to a large extent on the types of data that is being collected and shared. The ownership and control of the data continues to be a discussion, and really speaks to the governance of the data, how well it can be accessed, the security and the privacy of the data, and increasingly we've seen examples where data can be re-identified using not only the prime source of data, but other related data sets that can in fact be linked and then help re-identify. And one of the important aspects is, what's the interface between clinicians and data science? Because that's what's going to influence our ability to translate and implement and move from assist to augment to automate, as Anthony was talking about, and to change our behaviors. Because I think the human interaction is vital, and certainly around human factors engineering in terms of the inception of the problem we're trying to solve, how you're going to analyze it, the output, and the impact that has to be a continual theme throughout. And certainly swarm intelligence is an example of all of this being incorporated. I'm going to stop at this point and move on to our first speaker, who is Dr. Neil Sebai, who's professor of pediatric pathology at University College of London, Great Ormond Street Institute of Child Health. And he's the Chief Research Information Officer and Director of DRIVE, Digital Research Informatics and Virtual Environment at Great Ormond Street. Neil, thank you for joining us. Over to you.
Thank you very much. Thank you, Peter and Anthony. So I'm just going to, in the next sort of 5 or 10 minutes, really pick up on lots of the points that you raised from the perspective of the architecture and how we might go around trying to move from silos of data into reusable pipelines. And I think one of the things, so one of my other roles for one day a week is I work for HDR UK, which is trying to coordinate health data science kind of across the UK. And we just see this problem over and over again. So just to give a little bit of perspective, I think one of the things that's being increasingly recognized is there was a lot of excitement a few years ago around saying, all you really need is your EPR system and we can get the data from that. But everyone is now recognizing that that is one source of the data. Firstly, it's usually highly proprietary, and EPR systems are designed to manage patients. They're not designed to provide data in the format you may want it. The other thing that's being increasingly recognized is that the EPR will simply be one relatively small source of data for what you might want to do. And this was going to be touched on a lot, and not just the physiological data that you talked about, Peter, but also the new data sources that have not traditionally been in healthcare. So home monitoring, wearables, IoT, smart hospitals, etc. And the issue is, at the most simple, where are you going to put this stuff and whose job is it going to be to deal with it? So the sort of middle ring of this target here is the idea that there has to be some kind of platform for every organization that wants to make use of this data around the prime role of being data engineering and data curation. So that sort of management perspective. The other thing is that, and I think when we first started getting into this area a few years ago now, completely really underestimated this, is in the broad area of technology-enabled medicine. So everything that is really around AI, data, advanced analytics, etc. It is huge and ever extending, and everything is exciting. So you kind of end up going, oh, that's good, we should do that. That's good, we should do that. And actually, you quite quickly realize that you can, whilst there is crossover, you can identify kind of buckets of what you want to do, whether this is around clinical informatics. So by that, I would sort of encompass all the things around clinical decision support. What is required from that is very different to what you might want for computational biology or bioinformatics or data from devices, etc. So whilst all of these areas need some form of data curation and data engineering, and that's the part we're focusing on today, the specific requirements are very different depending on whether you're thinking about doing digital health in the population, app development, etc., or whether you're at the other end of the spectrum. And that definitely is something that we, I think, underestimated initially. The other thing more generally is that we are not good as a community at reusing data. And what tends to happen is an organization, a specialist hospital somewhere, will spend a huge amount of time and money curating a data set for usually not just one research project, but a research program, which will have some PhD students and some publications. But actually that will be independent of many other places that are doing something similar, or even in the same institution. And the general concept of saying, actually, can we move towards making data more reusable, so fair data principles, certainly in the UK, and I think globally now, but many of our big funders are now pushing extremely hard up front to say, how are you making your data fair? Otherwise, we are not going to fund you. And at the moment, the prime focus on this is on the F, which is the easy part. Still difficult, but relatively easy. So if you wanted to know who has data worldwide, who is collecting device data on asthma, you should be able to do that like you would do a Google search instantly. And actually, you can't at the moment. So one question for us as a community is, how do we just get better, even at the F? So forgetting all of the other parts of making it interoperable, etc. So that's definitely one area. The other thing that is, again, going along with that and is gaining a lot of traction in the UK, and I think, again, this is going to be globally, is around what's been dubbed the 5 safes from the Office of National Statistics. But this is around having checklists of how that whole data and research and project is being used. So it's not just around making the data de-identified, for example. It's around who approved the project, who are the users, what's going to happen to the data afterwards, how are those outputs going to be shared, etc. And in general, we as a community have not generally been that good at the concept of explaining how the analysis was done. So when you write a paper, you have to make it nice and slick and short, and you say, we collected the data here, here's what we did, and it comes across as if you did it all in one afternoon and it was super, it worked out exactly as you wanted. In reality, there are numerous steps, and the data that was actually used to generate those charts or plots or analysis was not the data that came off the machine for various reasons. And we need to get better at how do we represent that provenance to each other. And just picking up on what both Peter and Anthony said, there are huge areas to work on around standards and interoperability. And this is my personal kind of area of interest, certainly from the HDR UK perspective, is just asking some very simple questions around, for example, what to collect. So not even getting into details of how you store it, what's the data model, what terminology you're using, but what thing are you collecting? Now that sounds a simple question, but we tried in the UK when the COVID emergency was kind of starting to just say, all of these COVID studies, what are they collecting? And it was almost impossible because most of the studies were collecting a set of data elements that the PI of the study decided would be a good thing. They would start up Excel or whatever it happens to be, and they would go, oh, we're going to collect systolic blood pressure. If we're collecting systolic blood pressure, why don't we call it the same thing in every single research study across the world and define it in the same way? But even in something like COVID, we were trying to look, for example, at ethnicity, and almost every study, there was about 15 or 16 different data definitions, data dictionaries for ethnicity. And many of the studies weren't using any known data definition. They had just made their own classification up. And this is a major, major issue, not just for how we develop models, but much more importantly for how we deploy and evaluate them. And I'm going to come on to that. So just as a general principle, there are really three things we need to do to get value out of health data in general, particularly for AI. The first is to recognize that without investing in this kind of infrastructure to know your data and be able to deal with data in a scalable way around standards, interoperability, data models, definitions, etc., we cannot do this. The second thing is around recognizing we cannot do this alone. If we're going to want to work on something to do with, for example, computer vision, there are many tech companies that are already working on computer vision, and we in healthcare need to work with them. By far the trickiest problem, certainly I'd be interested to hear what others think, but for us in the UK, is the bottom right-hand corner, because the other two, if you gave me enough money, I can solve those. Be hard, but they're solvable. The problem is, this is nobody's job in most of the healthcare organizations. The whole thing of managing the data, the infrastructure, data curation, algorithm development, algorithm deployment and evaluation, these are all new jobs that don't generally exist in many places. And that's a major, major problem. So in general, the concept is that we all recognize that you need some way of bringing together disparate data sources. You need to do something to the data, and we need to move away from having silos of curated data into common ways that as a minimum, each organization, but ideally each country or specialty can start to deal with data in the same way. And we also need to think similarly about the analytics platform. Because to make these things scalable and transferable, we need to use tools that do not require highly specialist tools and analysis that only works on one platform. And I put this slide on purpose, not so much for this kind of audience, but just generally to make people recognize that data curation is often bundled up as one word. People kind of think, oh, this is quite easy. Can't you just employ someone to clean the data? But actually, there is a massive amount of skill and requirements for how you do this properly. And this may be around things like linkage, things around provenance, things around metadata, for example, and it needs to become much more professionalized. So I'm not going to go into any details of this, but the concept really here is that you do definitely need to move from having these kind of silos into the concept of having cloud-based trusted research environments. Now, there are lots and lots of different architectures you can do for having that, but the concept then is that you allow two things. You allow scalable compute, scalable storage, and you allow easy movement of data, but more importantly for the future, you allow potential for federated analysis. But with this comes all sorts of problems. I'm just going to give you one story before I finish. So we spend a lot of time bringing our legacy data into a common data model because we, over the years, have used multiple different systems, let's say lab systems, all of which store hemoglobin in a slightly different way, or creatinine, they call it a slightly different name. So we've mapped it to a single model. The problem now we're finding is a researcher comes and they go, we would like all the lab tests on this patient, this group of patients. And we say, do you really want that? And they say, yes, we really want that. And they end up with thousands of rows of data. And that's not what they were expecting. They were expecting a nice table that looks like Excel. And we absolutely realize that there is a missing link around translating the data request from the researcher into what is the actual data requirement for the data scientist and the engineer. I'm going to skip over some of these, but the concept here being that even if you don't do anything super clever, just by bringing the data together, for example, this is all of the lung function tests in the lab system over 10 years that you can show to a clinician immediately. And on top of that, if you make the data start to look the same, as in the structure, you can start to build tools. So we use R and R Shiny. This is an R Shiny app, which means that essentially live in real time, you can get a whole load of statistical comparisons and data analysis of any cohort of patients you want, because the data starts to look the same. So you can now start to make this reusable. So I'm going to finish here, but just really with these sort of 3 questions. So the first is, there is a lot of hype in the UK at the moment about, we have all this data in the NHS, isn't it great? It must be worth a lot. But actually the question is not, do you have the data? It's, do you have the data in the format it is required to do something useful with it? And those 2 things are very different. So there is a significant data engineering piece here. The second thing is to understand, building on from the introduction that Anthony gave, what are you now going to do with this data? So what tool are you using? What question are you answering? Because actually, the data engineering that's required may depend on what tool you're going to be using. And the last and absolutely most important bit from a clinical perspective is how you're going to deploy this. Because there are example after example of what looks like a great predictive AI or machine learning model that a team comes up with, and they're very proud of themselves. And it turns out that it was based on a data set that they have curated over the last 2 years for this purpose. But actually, when you say, how will this work in my hospital? They look slightly blankly and say, well, that's not really my problem. This is the data we based it on. And until we can start to have things that are transferable, we're going to continue to have these problems. So I'm going to leave it there, and hopefully just to have raised some of the questions. So thank you very much.
Neil, thank you. That was very insightful indeed. There's questions that have come through for you, but we'll wait until the end of the session and bring it to the panel. But thank you very much. It was a wonderful overview. Our next speaker is Dr. Sudhen Desai. Sudhen is Director of Research and Interventional Radiology at Texas Children's Hospital and Baylor College of Medicine. Sudhen, welcome.
Thank you, Peter. Let me try and share my screen here. I can't start the video. Oh, here we go. Can someone confirm that these are visible? Great, thank you. So Peter, Anthony, and the rest of the AI Med team, I thank you for the opportunity to speak here. As Peter mentioned, I work at Texas Children's Hospital, which is the largest freestanding pediatric hospital internationally, I believe, and I've been involved with some of our initiatives here over the last couple of years. I do want to note that there's a countdown as they are summarily dismissing me in the next couple days. So I'll be starting a new endeavor out in Phoenix. I like to show this because this slide definitely speaks to the caliber of the folks that we have here and chime in on AI Med. I do think that this far side cartoon, for those of you that have seen this in the past, also illustrates some of the conundrums that we face in terms of having to take a step back and look at a global picture as opposed to some of these microscopic pieces of data, and because there's just so much. I don't want to berate the points that have been covered in detail. We all, by attending this seminar, understand the value of having technology involved in the care of our patients. Patient outcomes, health surveillance, healthcare policy decisions, getting to a point of data-driven medicine and removing emotion out of decision-making. This all makes sense. And particularly in the world of radiology, and we're going to segue into pediatric radiology here in a second, The number of publications devoted to this has just markedly and exponentially grown over the last few years. There's open data sets for training sponsored by the NIH and the Radiology Society of North America, or the RSNA. And multiple institutions now have created standalone journals just focused on artificial intelligence, similar to the one that Anthony edits, as well as radiology. And RSNA now hosts an annual AI challenge, some of which are listed here, with particular note of the pneumonia and the pediatric bone age specified as a result of their relevance to the pediatric imaging space. So what is the value proposition in pediatric radiology? Well, why does it matter that we spend time in the pediatric space? Because as we get to some of the challenges, we realize, and Anthony has touched on this a little bit as well, that working in pediatric radiology in the pediatric space is not necessarily analogous to working on the adult side of medicine. So for the kids, what do we think about? Well, scheduling inefficiencies. We want to reduce NPO times and therefore reduce the burden on families, because most of these children, particularly children the younger they are, will require anesthesia support. We want to improve patient throughputs, reduce their exposure to contrast medium and scan times or PET radiopharmaceutical exposure. We have a real issue with image enhancement. So sometimes we retake images multiple times because the patient in the pediatric space is not able to hold still. And we want to remove or reduce these anesthetic exposures as much as possible, particularly in the cohort that's less than 3 years old. There's an FDA label that goes, that our anesthesia team always communicates to every patient in this age group, or every family of a patient in this age group, in order to warn them that, you know, there are some potential longer-term neurocognitive impacts. We don't know what they are, but it sparks concern for the families and therefore, you know, engages conversation. So whatever we can do to reduce the morbidity of pediatric diagnostics is absolutely useful. So what are the challenges in a pediatric radiology environment? Well, we all know data is king. And so freestanding children's hospitals suffer from the ability to uniquely aggregate enough data to train models, and that is simply because of the patient volumes and throughput. We so far have not enacted large, open, publicly available data sets to foster specific AI training within the pediatric radiology space. And I want to point out a few things here. From a resource perspective, these freestanding children's hospitals are organized differently than most of your traditional academic medical centers. They tend to lack a strategic, interoperable, and agile enterprise IT infrastructure, some of which Neil touched on just in the prior talk, because their heavier focus is on the information systems, the PACS, and the EMRs as functionally integrated systems. But this makes it difficult to transfer huge swaths of data throughout the institutions, and therefore this need to create the architecture abounds. And I think it's safe to say, as was previously pointed out, we don't necessarily contain that expertise internally. Additionally, when we look at pediatric imaging, the images overall are smaller, but there's a greater amount of anatomy presented. So we think about an adult chest X-ray versus a pediatric CHAB or a chest abdomen, which covers a lot more space of the patient. So as we get into data processing, you now have to have algorithms that are able to discern much more than just a chest X-ray. Now, obviously, you know, we do take pediatric chest X-rays, but there are variances in terms of image acquisition techniques that we need to pay attention to. Additionally, this definition of what is normal in the pediatric space versus pathologic is going to vary based on the stage of development. So if we just take a look at plain radiography, the normal in a 2-year-old versus a 12-year-old versus an 18-year-old is going to be drastically different. So the algorithms need to account for that. The data training needs to take place to allow for that. but it requires increased segmentation of the data flow, and therefore the architecture potentially gets more complex as we move into some of these areas. So, an example, what is a growth center versus a fracture fragment? What is a nutrient channel versus a fragment? All of this, which brings to point, pediatric radiologists by and large tend not to be data scientists. And therefore, this expertise, again, as has been mentioned, we look to external sources to provide. So Texas Children's has about 700 pediatric beds throughout the enterprises. There's 3 hospitals and a multiple number of freestanding outpatient clinics that also have imaging capacity. Most of the volume that we focus on, particularly with respect to this subject, though, is related to our emergency department. How do we figure out which films are most important? You can see that of the almost 200,000 radiographic examinations obtained in 2018, about 40,000, somewhere roughly in the range of 20%, came out of the ERs. In addition to that, there was almost 16,000, there was a little bit over 16,000 CT scans and close to 21,000 MRI exams. So that's at our freestanding institution. Now, these numbers are significant, but if we start to break them down into what their components are, we begin to realize that each individual exam doesn't have the data behind it to support some of the endeavors that we talk about in the AI space. And additionally, I'm going to just gloss over this, but why do we protect this patient data? What is the goal of that? And it's important as it relates to this discussion. Well, there are legal components of this with the HIPAA enactment in 1996, and then the omnibus that was passed in 2013, which actually in part wanted to address the digital components of patient data. Europe has also enacted their own legal structures. And then I think there's an ethical component to this, which will also be expanded on later. But this data, at its truest form, belongs to the patient. And these patients that we're talking about have lifespans potentially that will cover 8 decades. So how do we ensure that the data is appropriately utilized, protected, as we try to achieve some of the goals of AI in the imaging space, but also make sure that it doesn't come back to haunt us on the development side and the patients on the recipient side later on. So I want to touch briefly about a project that went through our system. This was purely on the research side. It was a non-clinical activity, but the data was reviewed from over 21,000 pediatric elbow examinations, encompassing about 59,000 images that were acquired over about a 4-year span from January of 2014 to December of 2017. Approximately 20,000 of those studies were utilized for the training set, and the remainder were used to validate. Again, only for research purposes, not for clinical implementation. And we see here the subcomponents of the imaging exam that were processed. And I think, Neil's point about how the data is delivered is critical, because in imaging in particular, you can see with the AP view of the elbow, that middle image on the left side of your screen, we don't always get stuff that is at a horizontal or vertical orientation. Some of this stuff comes at us any which way the technologist can obtain it. And so it's incumbent on a pre-processing program to put it into a form that's usable by the algorithm as it goes through the processing. And we were able to achieve an RUC of 0.95 with reasonable accuracy, sensitivity, and specificity. Now, again, this was for research purposes only. It was not clinically implemented. But the point is that we could start to classify an entire series of images instead of just making classifications based on single images. And this begins to model the image analysis algorithms that radiologists undertake. Now, this came out of our basic science lab of Dr. Anna Pragala, And we are talking about how to clinically push some of these algorithms forward. So there is significant data in pediatric radiology. Us being one of the largest freestanding or the largest freestanding pediatric hospital in the world have greater access to some of that. But I think Anthony's point about needing collaboration between institutions is spot on, because as we move forward, we need the institutions to work together. I think not only from the standpoint of data generation, but removal of bias, et cetera. We want to capture meaningful volumes of this data and allowing development to take place, but we need to focus on the same issues that have been addressed in some capacity on the adult side, data security, ethics, et cetera, all of the things that are important to this patient population. But we all understand that there's a significant upside if we're successful in navigating some of these waters. I think particularly in the pediatric space is important, and we really need to focus on the how we do it so that we do it right. Thank you.
Good, thank you, Sedan, very much. It was a very insightful view again as to radiology specifically, but also broadly applicable across the field of data engineering and data science, to use Neil's terminology. Our next speaker is Dr. Sharitha Reddy, who's a clinical assistant professor in pediatrics and pediatric cardiologist at Stanford University. Sharitha, thank you.
Hi, thank you. Let me go ahead and share my screen. Is this visible to everybody?
Yes, it is.
Okay, perfect. So this is a perfect segue from Dr. Desai's talk, actually, because I'm going to be talking about something similar, and that's about looking at how we can bring together cardiology data, non-invasive cardiology imaging data into a collaborative. And so I'm talking to you today about something called Chamber, which we're working on at Lucille Packard and hoping to collaborate with other institutions. So many of you already know this, being kind of in the pediatric field, but something I always like to point out is that adult cardiology and pediatric cardiology are extremely different. If you look on the left, that's kind of the typical adult heart, whereas we could spend forever looking at the different types of congenital heart disease, which obviously means the populations of those are also quite a bit lower than the adult populations. This translates very obviously into funding disparities for research. In a paper that was published looking at NIH funding from 2005 to 2010, the disparities are obvious. There were 116 pediatric cardiology trials that were funded as compared to almost 2,600 adult cardiac trials during a 5-year period. As many of you already know, that impacts the recommendations for pediatric cardiac management, as well as many other fields in pediatrics, in that the data ends up being anecdotal, based on expert opinion, or worse, sometimes extrapolated from adult literature. And this infographic kind of points out the hard numbers, which is that 16.5 million Americans are living with kind of typical adult cardiac disease, making the numbers of pediatrics look quite small in comparison, where we see that 40,000 babies are born with congenital heart disease each year, 25% of which will need surgery within the first year. But in general, the numbers of children and adults living with congenital heart disease in the US at least is 2 to 3 million. It's still a high amount that we can certainly be impactful with, but pediatric cardiology, among many other fields, have found ways to really approach this problem of smaller populations not getting appropriate funding and really trying to use a learning collaborative approach. The approach that's been taken up is by using collaborative and transparent data sharing in various formats. So focusing on a diagnosis or a certain time in the patient's hospitalization. So the few images that I have here are actually of different collaboratives just within the field of pediatric cardiology. One of them focuses specifically on patients with hypoplastic left heart or single ventricle physiology. One of them focuses specifically on patients after surgery during their time in the cardiovascular intensive care unit. Another looks at data of patients immediately after leaving the ICU during their time in the step-down unit. Another looks at neurodevelopmental outcomes for many of our children with congenital heart disease. The benefits of the learning collaborative approach is that there's data sharing amongst multiple institutions, allowing the data pool to be much larger. There's an opportunity for quality improvement. And in some instances, they've been able to come up with a standardization of both surgical or post-surgical approaches that can be then deployed across all of the institutions that are participating to really see a potential impact for patients. These have been successful, but one of the issues that I think has been brought up multiple times is that the data exists in silos. And so one of the approaches that's recently come to fruition is the Cardiac Networks United, in which now a centralized group has allowed these institutions to stay separate, but serve as a data aggregator such that each collaborative can actually share and send data back and have access to the larger group, even if their individual collaborative isn't collecting that data. So from a pediatric cardiology perspective, what's missing? And for us, that's the cardiac imaging data. The echocardiograms are the first line of diagnostic testing for any patient that basically walks through the door. It's non-invasive. We use it for anatomic determinations, for diagnosis. We use it to assess ventricular function, not just in patients with congenital heart disease, but oncology patients, nephrology patients. We use it to guide treatment management that's within cardiology and outside of cardiology. We definitely use it for surgical decision-making and just for overall maintenance of patients. MRI is also part of this. It's a major part of our field, definitely more expensive and less frequency, but it's a very, very valuable source of diagnostic testing. So the potential for using AI and machine learning algorithms is high. And I think the way that we think about it in the field of echo is that there's really two broad strokes. One is the ability to automate the tasks. So that could be image selection or optimization, meaning when somebody puts a probe down right now, our very experienced sonographers have to be, again, very experienced in order to find the views that make sense. In pediatrics, that can be challenging. We have infants that are moving quickly, the heart rates are quicker, the resolution is better, but there's a lot of variability. We also take care of patients with a huge range of weights and heights that can affect the images. Measurements of various structures. So whether those are structures that are, valves or arteries that we're measuring the actual size of versus the function. So assessments of volume and ejection fraction. And then the second, I think less focused on, but is the bigger possibility, is the discovery of clinically important insights by looking at novel markers. So this is a little bit of what Dr. Chang was talking about regarding unsupervised learning, but kind of finding things that the human eye is missing or that patterns that we haven't recognized. So novel markers of looking at cardiac function or to use for risk stratification or predictive modeling. This work is already being done in the adults and has not been really done in pediatrics as of yet. And this is just an example of, how many studies have come out just over the last 4 to 5 years looking at adults, looking at adult echocardiography, but has not trickled down at all to pediatric echo. So the goals for Chamber are really to create a data ecosystem for pediatric cardiac imaging data, to create a machine learning research infrastructure, and to build partnerships with existing learning collaboratives to avoid the silos of data that have been brought up multiple times. This is just to talk about how the input would be pediatric and fetal echo imaging and reporting data. So not just the reports, but actually the physical images, to a centralized storage and computing location, and then to have a machine learning and research infrastructure at the end. This is somewhat of a busy slide, but it shows the concept of how we propose to do this, that the data exists at the individual institutions. The idea is to anonymize kind of at the level of the institution, feed the data into a centralized data pipeline where it will be stored within a secure data ecosystem. This model has been done at Stanford for population health sciences, so not to the extent of large imaging data, but has been done such that multiple institutions are sharing this data. The idea is that here, data storage and labeling could be undertaken. So whether that's for measurements, report text, labeling based on demographics, diagnosis, outcomes data, and report text and data aggregation. In addition, some services that would be provided would be the computing and network servers. At the end, there would be a user interface that is more easily accessible to clinicians, not just machine learning engineers, but to have the availability to be used by both, with the plan to to be able to find data sets that are much larger than what's present at an individual institution, to be able to explore and cut cohorts, to perform statistical analysis on these cohorts, to design and run machine learning algorithms, and to store and publish these algorithms and data sets. Now, the question remains as to how do we actually acquire this data from multiple institutions? I'll talk a little bit about the issues in some upcoming slides, but we've approached this in kind of a two-pronged approach. One is looking at using the edge server capabilities. And what that means is that the data can be pulled directly from the Echo machines. This calls back to what Dr. Chang mentioned in the Pediatric Cloud project, where machines can be linked to each other. And so in this setting, the data exists on the Echo machine. We can pull the ultrasound directly off of the machine, anonymize at the edge server, and then transfer to the center cloud. Now, the advantages to this is that all of that work can be done on the individual machine basis. It's a faster implementation to a certain degree, and it still allows for safe anonymization. The issues with it, or the cons, are that it would not include any of the offline measurements or reporting data, and it does require a physical device on the ultrasound machine, and it would only include prospective data. Now, these are some big issues, but I think the biggest important thing to think about is faster implementation and how that works. On the other end, it would be the more traditional route of obtaining the data from the existing PACS servers. And so what the traditional model that most hospitals have is that from the Echo machine, the ultrasound is transferred to a server where both reporting and measurements can be done. And these include the offline measurements. And then the report is published. If needed to send for research projects or things like that, there's usually an additional program required to anonymize the data and then send it to a center cloud, or in many cases, what we're doing right now is send via a CD to other institutions. So the other approach is to access the data from the PACS servers directly, which would be a richer data set, including the measurements and the reporting text. The challenges with and so it would include both retrospective and prospective data. The challenges with this method is that each institution has disparate PACS systems. They don't all communicate with each other. The data isn't necessarily organized or standardized in a certain way. In addition, because most of the PACS servers exist as part of each university, it requires a significant institutional infrastructure support, as well as significant cost, and maybe even more buy-in from each institution to alter this, as well as approaching each institution as a separate challenge. I think the impact for patients is obvious. I've listed a few potential use cases looking at both automation, prediction, and risk stratification. But if we just think about very basically left ventricular size and function, as we mentioned, that could impact oncology patients, renal patients, any patient with a family history or existing cardiomyopathy, transplant patients, rheumatic fever, Kawasaki disease. Looking at right ventricular function, And these are in anatomically normal hearts. I haven't even completely touched on significant congenital heart disease, but looking at pulmonary hypertension, our neonatal patients with BPD or congenital diaphragmatic hernias. The other areas of potential impact are prenatal detection of congenital heart disease. We do fetal ultrasounds to diagnose congenital heart disease quite often. And one of the challenges that still exist is missed diagnoses of these. The other is thinking globally. In non-expert hands, there's still a role for ultrasound, especially point of care ultrasound. So what are the benefits of automated guidance of image selection in those patients? So it should be simple, right? We want the solution. People think it's beneficial, but that's not the case. So as we think about considerations, I wanted to bring up a few points that have been brought up before, but specifically tied to this venture. So one is the implementation and data management. So the actual physical infrastructure, who do we need in order to actually get this done? So it requires a huge team of people. Just to do the research project, you might need a collaboration between data scientists and the clinicians, but in fact, the actual infrastructure of grabbing the data, building all of that is going to require large teams of IT, engineers, storage, and vendor-specific issues that come up with each different hospital or institution that's participating. The other question that comes up is, should the data be centralized or decentralized? How do we manage that? Individual institutions, do they want to manage some of their own data? Are they willing to share? Are they not? Security obviously comes up quite often, which is how do you anonymize the data? And the big question now is, in combination, if you're talking with if you're utilizing services such as Google Cloud and things like that, is there a risk of deductive PHI? Are the normal methods of anonymization enough or not? And then funding is a big issue. Who funds this? What are you beholden to when there is funding from somewhere? Data quality, which was brought up in an earlier talk. In this case, we have significant clinical and image quality heterogeneity. Not all institutions follow the same protocols. Not all institutions require the same level of quality for each of their imaging. Depending on the source of the imaging, the machines are different. And so this obviously creates a huge amount of variability. That being said, you want to make sure that that any results of these are broadly applicable, not just to the perfectly curated data from a certain data set. And then the next is, how do we make the data as powerful as possible when we want to integrate it with other data sets? Just having echo imaging data, while powerful in itself, I think will not mean quite as much if it's not included with the rest of the clinical data. Some other considerations that have come up during the planning of this are participation and incentive as well. Something that I have coined collaborative burnout, looking at just the institutions that are participating right now in pediatric cardiology. They all have there's buy-in to each of those collaboratives. They require a physical person to actually enter in the data, and the outcomes can take quite a long time to actually prove. So many institutions feel, are the benefits worth it for participation? Data governance, looking at how it's managed, open access versus not. Intellectual property, this is unique in that machine learning algorithms can generate that. Is there a monetization? How do you approach that? At which point do you involve various vendors? And then something that was brought up earlier is really the ethics of AI. How do we validate the data such that we know we're removing some biases, making sure that it's viable for all patients that it's meant to involve? And who takes responsibility for the actual administration of these algorithms and any outcomes that may come of that? So in answer to those things, we thought a little bit about what our current state is. And so we don't have the answers for all of them, but this is how we've approached it thus far. So the implementation and data management, as of right now, we're piloting in 3 to 7 hospitals with the two-pronged approach we describe. One is the completely prospective only imaging data via the edge server, and the other is to approach the slower process of the PACS servers to get the rich retrospective data. We've had the luck of engaging with startups and hospital IT. and the benefits of university partnerships for computing, storage, and machine learning. We have approached both philanthropic funding and research funding for our funding.
Sharitha, we're just bumping up against time here, please.
Okay. For data quality, the last part is that we are talking with early partnership for other collaboratives to share the data. And lastly, an automated process to avoid burnout and a phased approach such that there's tiered access and eventual open access is the hope. I don't think anybody solved the ethics problems. And so we just return to our mission, which is to improve outcomes in our fetuses, children's, and adults. And that's what keeps driving us forward with these projects.
Good, Sharitha, thank you very much. That's very comprehensive. And we can see common themes across all of the talks, can't we, around the problems up front with the data acquisition and all components of how we manage it. Our last speaker, Spiro Moussos, it's great to welcome you, Spiro. PhD in molecular genetics and has a huge amount of experience and research in systems oncology and biointelligence. Spiro, it's great to have you join us.
Thank you, Peter. And I'm going to keep, I won't show slides. I'll keep my comments short so we can get back on time here. But let me just say that at Systems Oncology, what we're doing is tackling a very important paradox in data. You heard from a lot of speakers that gathering the data and organizing the data and making it accessible has been so far a big limitation. Well, in oncology, we are very fortunate that we have this plethora of big data now. So thanks to advents in genomics and genomic sequencing and omics in general, we now have more data than we've ever had in the past to discover new insights into cancer biology, personalized medicine, and come up with new therapeutics. The paradox is that with all of this new data, we're not developing drugs that are making a significant impact in patients' lives. Now, why is that? So certainly there's a lot of discoveries, and there's certainly a lot of new molecules and a lot of diagnostics that are coming up. But if you actually look at the improvements and outcomes, in some pediatric cancers, we've made tremendous progress. But in cancer in general, especially in late-stage oncology, we're not making that much progress. So we've taken on that challenge and said, well, why is this paradox? Why is it that the more data we have, the more expensive the drug development becomes, to the point where it costs more than $1 billion now to develop a drug through NDA? And not only is it more expensive, but it's less effective and less efficient. So we believe that that's a problem with data interpretation. In fact, imagination. So humans have no problem translating disparate types of information into something that could be useful. Our human brains have a hierarchical network that allows us to abstract higher order concepts. When we try to do that with genomic data or with protein interactions or clinical data, we store it in databases that don't allow those kinds of hierarchical networks and don't allow the kind of modeling that's required. So what we've done is solve that problem. And the solution is very elegant and very simple. It's hypergraphs. Hypergraphs are like binary graphs, except they have special properties. They allow for multilateral, multiscalar, multidimensional networks. And these networks have enabled us to represent knowledge in a completely different way, in a way very analogous to the human brain. So we see it as cognitive computing because it uses hierarchical networks. But when you apply that with machine learning, we're now able to generate new hypotheses in the same way that the human brain can generate hypotheses. And that has been a real breakthrough in our ability to translate big data into meaningful, useful elements that could be turned into hypotheses that could be tested very rapidly into the laboratory. So that's what we've done recently. We've been able to, in the simple use case, we've been looking at the synthetic lethal interactions. We've mined the TCGA data, which has whole genome sequencing data on 11,000 patients. So whole genomes times 11,000. And we've integrated that with trillions of connections to protein interactions and so forth. And we were able to find new therapeutic targets that were far beyond what anyone could imagine. The reason they couldn't be imagined is because the human intelligence can only come up with a small number of hypotheses to test and can't map them to big data. So we've been able to, on scale, test billions and billions of hypotheses and identify the ones that best map to the data, and very quickly identified novel drug targets. So that's where we are today. We think that hypergraphs are something that could be very useful for integrating any kind of healthcare data. It's worked for machine learning and drug discovery, and we think it could really transform healthcare as well.
Spiro, thank you very much. That's looking to the future as well, but another tool that we can apply to this huge amount of data. We have 5 minutes for questions. We have a hard stop at 12:40 Eastern Standard Time. There is a question here, if I can start, Neil, around the data dictionary. And perhaps you can elaborate on the NHS efforts in that regard, please.
Yeah, I'll answer this very quickly. So the question really was around, because in the UK, we, in theory, have a national health system, it should be easier because is everyone collecting data in the same way? And the short answer is no, as you would expect. The slightly longer answer is that there is an NHS data dictionary, which is actually pretty good. Maps to SNOMED CT and various other things. And in theory, if everyone used it, it would be very beneficial. In practice, like in many countries, this is almost entirely used for billing and activity purposes and mandatory reporting. And anything that is not mandatory tends to default back to whichever is the standard that the IT supplier for that organization uses. And we have such a mixture of different EPR systems and other systems across the hospitals that it is still a major problem. So unfortunately, the short answer is, whilst in theory, yes, in practice, no. But I'd be interested to hear what other countries' experiences are.
Well, I know in the United States, we don't have a standardized way to do it as well, and it's a continual problem. So much of our time up front is spent with the data is trying to get the appropriate libraries and definitions so that we can have a reliable data set in which to use. And that is a problem. Also a problem with vendors who have their own nomenclatures as well. So bringing a consistent language across, I think, should be part of the overall goal here in terms of interoperability. Another question related to the use of data external to our own enterprise. We've heard about it within our own systems, within healthcare, and within collaboratives. But data out onto external platforms in the cloud. Boston Children's Hospital has a relationship with a company, according to one of the questions here, with a company called Trinetics. But the transfer of data out of clinical healthcare environment to the cloud to another company who then manages that data. What's your thoughts around that, Neil? And then the others, Sudan and Sharitha as well, for your own data sets.
So this is very topical in the UK at the moment. The good news is that, so until 2 years ago, we weren't allowed to store any healthcare data that was outside an NHS cloud. We couldn't use public cloud, but actually now with the appropriate security, et cetera, requirements, we can use public cloud. So that makes a big difference. So for example, our platform is now all moving across to one of the big commercial vendors. The issue, the cloud makes it a lot easier to do lots of things with large volumes of data, federated analysis, etc. But because it makes it easier, it pushes forward the governance and not just the governance issues, but as it's been mentioned, the sort of value from the data, not really ownership, but who gets the value then? How do you do if there is IP that comes out of this, how do you appropriately split that? And this is for us, it'd be interesting to hear what the other speakers think, a major issue around when you do this distributed approach, because you might get one hospital that puts in, I don't know, 300 cases and another hospital puts in 10 cases. does everyone just split the value, and how do you do that? And the quality may differ. So how do you then take account of that? So it'd be interesting to hear what the others think of that.
Last 30 seconds, Sudan. Sharitha, do you have a comment?
Sharitha.
Yeah, so I think the way that I don't think that there's been a clear solution, and I think that's part of the issue. One of our ideas is that it would be used to really fund the organization all over again if there was intellectual property, rather than trying to split that amongst all the different institutions, because we are similarly using, commercial vendors as well, but through a university contract.
Thank you. Well, this is a rapidly evolving environment, isn't it? I want to thank all of the speakers for their contributions today. And I'm sure that this is a topic that will come up and continue to come up as we evolve over the years ahead. So thank you very much to each of you. I really appreciate you being here. And Alexis, over to you as we start the networking break. Thank you, everybody.
Thank you, Peter.
Thanks so much, Peter. An excellent panel. And yes, we are now going into a networking break. The way that will work, if you have a look at the top of your event platform screen, you will see Social Lounge. Click on that tab and you can select from one of the two options. And we will be back here in 30 minutes for the next session. Thanks again.
Welcome back, everybody. Hope you enjoyed your break, networking break. And it's my pleasure now to introduce Dr. Hamilton Baker, a friend and someone I met on this AI to medicine journey. So Hamilton's really come along in a remarkable way personally in this journey. So I asked him to moderate the session on machine and deep learning. Hamilton.
All right. Hello, everyone, and thank you for that. Yes, I was just going to do that real quick there. Terribly sorry about that. All right, getting started here. Thank you, Anthony, for allowing me to participate in this conference, and to AI Med and all the fantastic minds. So starting off like any good presentation about AI, machine learning and data science, using a Venn diagram, of course. And this is a relatively simple one, but okay, I get it for you here. Do you see it now? Okay, great. A relatively simple one that just sort of explains where deep learning fits in the context of machine learning and artificial intelligence, in that it is a subset of machine learning, and machine learning is a subset of artificial intelligence. Artificial intelligence has become an area that's just so large and hard to define. Deep learning is actually a relatively specific part of it. In my own journey through this process, I came across another Venn diagram that I really liked, and it's this one. If you've looked at data science and what it is, how is it explained, you'll often come across this particular diagram. It's frequently filled in even more specifically in the subset areas of it. But I think it really, in its simplicity, this particular version shows you how important those three domains, and that is coding or computer science, statistics, which includes mathematics as well, and domain knowledge really have to come together to create data science. And in my own experience, trying to learn more about these, I certainly considered myself somewhat of a domain knowledge expert in the area of medicine, but these other areas were quite intimidating when getting started in machine learning and deep learning. And I think that even to master one of these areas makes you sort of a ninja in a certain way, because if you can really master one particular domain, these are all very complex. However, being able to bring them together and master all three domains, that really truly makes you somewhat of a Yoda. I think what this illustrates is just how difficult it truly is to master all three of those domains. And in my experience, especially in machine learning and deep learning, what I've found is it's really more important to look at teams, and that teams in this setting are going to be more powerful than even the most well-educated and experienced data scientist who understands all three of those areas. And I think it's the combination of people that are trying very hard to educate themselves in all areas, coming together with their own special knowledge to make these teams. So to get moving along with this session, we're going to be hearing from some probably near Yodas in this area, and more about the great teams that they've put together. First, we'll be hearing from Dr. Randall Wetzel. He is a professor of critical care medicine at Children's Hospital of Los Angeles, and also a professor of pediatrics and anesthesia at the USC Keck School of Medicine, and as well as being the director of the virtual PICU. Randall, why don't you take it away?
Thank you very much, Hamilton. Screen sharing time. Can you see my slides?
Yeah, we can see them. You just need to hit present.
Is that good?
Yep.
Thank you very much, Hamilton. I'm going to talk about what the virtual PICU has done over the last, since its founding in 1997, several years. This is going to be a quick overview of applications of data science to understand how critical illness happens to children. Here's a brief outline: interpretation of EMR data, just as it comes from Cerner or Epic. And we started off clustering, moved into deep learning, do a lot of risk of mortality as a proxy for severity of illness, and improving how our recurrent neural network does, and introducing it to folks who may not be familiar with it. As Hamilton said, this is a team sport. This is rounds in our ICU, and as you can see, we have several data scientists who round with us. It's as important that they understand what we do as it is that we understand what they do. And if this isn't a team collaborative support, it is not frightfully successful. One of the first projects we did was a simple unsupervised clustering project using simple k-means. Always the hardest part is getting and aggregating and munging the data. But as you can see, simple k-means can take a group of 10,000 critically ill children, break them into a number of clusters based on their physiology, and that they have different characteristics or phenotypes in those clusters. As you can see, there's a group that has a high incidence of intubation and the rest don't. But you can also see group 7 here has a high mortality rate and that's pressor use rate and a high mortality rate. So you can pick out patients that have certain phenotypes within the ICU using a clustering methodology. We also did unsupervised pattern discovery in electronic healthcare, same model, using probabilistic clustering. In this case, it was a Gaussian mixture model to pick up groups of physiology. The first middle panel shows a low mortality cluster, and those patients are pretty close to normal or supernormal. And on the right, we have a high mortality cluster where the patient's physiology is demonstrated, and you can often see that it's quite far from normal, and it also has a great deal of variance. This led to us looking to causal phenotype discovery and using deep networks to understand which factors were contributing to the patient's ultimate outcome. This is a paper that we started to use a long short-term memory recurrent neural network to diagnose patients without any diagnostic information other than their physiology using their EMR record. And this is useful for finding patients that fit diagnostic classifications. And it performs in many instances better than the clinician data rate. So this is quite useful if you're looking for specific diagnostic patterns and you only have the physiology, to go along with the clustering that can give you phenotypes, not necessarily labeled diagnostic groups. We've moved on to using recurrent neural network, again, long short-term memory model. This is a very basic feedback loop that has vector inputs, as you can see down here at the bottom. All of the things that are available, we think about them in 4 categories, manages them, and has a output, which in this case is probability of mortality. This is a very useful model for looking at the temporal dimension, i.e. looking at flowchart data in our EMRs as critical illness happens to the patients. It can work on an irregular time grid, it can handle missing data and superfluous data, and it has feedback mechanisms that integrates previous information into the next time step. One thing that's important about RNNs, they're quite robust. And in the past, machine learning often required steps that included feature selection to try and either speed up or improve the performance of your machine learning predictions. But the LSTM is very robust. This is an experiment where on the top panel, we ran it with known data, but the bottom panel, we added uninformative extraneous features. And as you can see, it very little degraded performance. This is important because you don't have to worry about feature selection. In fact, we are now putting about 480 variables in, from blood pressure to echocardiographic parameters in some of our models. This is a continuous deep learning again, RNN, individual patient mortality prediction from admission. And we compared multi-layer perceptrons, a logistic regression, and RNN modeled on over 300 variables. I just want to point out that we can get at every step along the RNN a prediction of mortality. And as you can see, the top two patients are survivors. And if you look at, let's look at this panel, this compares the MLP and logistic regression. The bright blue is the RNN. The prediction of mortality varies over time. And as you see in this patient, the patient came in quite ill with an 80% risk of mortality or severity of illness. Got a little better, got worse again, but improved over time. This is about 5 days. And for the subsequent ICU time, these are times in hours, sorry, the patient had a very low risk of mortality. In non-survivors, you can see patients that arrive, maybe not so ill, but deteriorate. And you can see in general that the RNNs are more stable and frequently have better prediction earlier than do the other methods. It's also quite effective when compared to other standard severity of illness scores such as PLOD, PIM2, and PRISM, which are almost canonical pediatric ICU severity of illness scores. And this is looking at the area under the receiver operating characteristic before, following admission to the ICU, again in hours. You can see that there's a period of time where the RNNs pipe up and become stable. And this is before, this panel on the right is before discharge from the ICUs, whether they survive or not, this patient. And again, the AUCs within the last 24 hours are highly predictive of the final outcome and outperform the other models. This is a paper that's currently in press in Peds Critical Care. I just wanted to show these four sort of types of patients. This is time in hours in ICU admission, risk of mortality. We have a patient here in purple who comes in with a very high risk of mortality. It doesn't change, and the patient does not survive. Another patient that came in with a high risk of mortality was resuscitated. The risk of mortality fell nicely as an indicator of severity of illness over a few hours, and that patient survived. Another patient who had a low risk of mortality on admission, however, had an untoward event which increased the risk of mortality, resuscitated, and again did poorly. So you can follow individual patients quite closely. This is just a summary of that risk of mortality, the receiver operating characteristic curves. You can see that the RNN performs better than the MLP in logistic regression and the standard scores in predicting mortality with an overall AUC of 0.934. And this is again demonstrating the pipe-up period for the RNN to improve its area under the receiver operating characteristic. By 12 hours, it is quite accurate at predicting long-term mortality. Another thing that we worked on was to see if we could determine what an ideal, or at least a ready to be discharged from the ICU physiologic state was by looking at all of the parameters in the EMR and seeing if, and looking at the time period between when they were ready medically for discharge, i.e. the doctor said you can leave, they continue to be observed, and when they finally leave the ICU. So that time period gives us an opportunity to look at what their ICU physiologically acceptable state space, this is an n-dimensional state space that takes in all the description of their critical illness, which we can predict, and surprisingly within hours of their ICU admission. This may enable us to have personalized patient management targets, as well as apply other machine learning techniques. And the question we're always asking the ICU is, what's this child's acceptable heart rate or blood pressure or respiratory rate, or take a whole series of events? That varies highly individually from patient to patient, and using just age standards is not appropriate. How far, another question you can ask is, how far is my patient in this multidimensional space from the ideal physiologically acceptable state space? And that may give an indication for how we move him towards survival and discharge. This is just a diagram of that medical discharge to physical discharge. This is the acceptable, predictable space that we are trying to predict on admission to the ICU. So we have a standard for where we're trying to move and individual patient. This is a quick pattern of looking at 3 vital signs predicted within 3 hours of admission compared to age normals, a regression analysis, and the RNN predicting. And as you can see, the most satisfactory root mean square errors are in the RNN. So we get a pretty good picture of what the discharge status of the patient ought to be. We've also applied RNNs to a host of other predictive problems, and this one was just published in Peds Critical Care Medicine, using machine learning to predict cardiac death within 1 hour of terminal extubation. Patients' care has been terminated, and the reason this is important is there is organ transplantation in patients after cardiac death. This requires preparing the family, preparing the caretakers, preparing the hospital, preparing the operating room, and being ready to do the organ donation of that child. If they survive after extubation for several hours, that's not possible. So you want to know that your patient is going to be able to be an organ donor prior to going through all of the setup and putting the family through the questions. And we compared our machine learning model predicting time of death within 1 hour and found that it had a positive predictive value of 0.93. And on the patient's number needing to alert, looking at all of our DCD transplant patients, potential patients, that we could predict very accurately and predict who would not survive an hour and be a good candidate for DCD. We have generated a model based on this workup that is going to be an online prediction for anybody to use by feeding in the data. We've also wanted to improve the response time of the RNNs, and I'll just briefly mention this. We've developed something called a perseverating recurrent neural network that feeds current data in on a number of occasions at each time step. And I'll just talk about this, a survival prediction here. As the orange is the perseverated RNN and the blue is our standard RNN. And as you can see, when the patient starts to deteriorate, the time lag for our standard one is a couple of hours in this case, and even more here. But this actually allows us to more acutely, you want a timely prediction of how sick your patient is in the ICU, to stay much closer on prediction. I am going to just talk about one more thing. We have also been trying to interpret which features are important to our RNN's prediction. This is one model we've used. It's called a learned binary mask. We basically take our data matrix or vector and occlude part of the data, trying to drive the mortality prediction to 0 over here, and determine which features are important in determining mortality in an individual given patient. This is actually looking across the top 50 features in a whole cohort of critically ill patients, not an individual. But these are the features that are most important. This is the top 50 features. But if you look here, it's not surprising that these features are here as determinants of how critically ill the child is and his risk of survival. Some interesting things I didn't expect were patient's mood level, pain scores, quality of pain level. The rest of these are pretty standard, but obviously these markers in the chart we don't usually look at as indicators of not going to do well. You can do this on the individual patient level. This is a patient with a brain neoplasm. I won't talk about kernel SHAP. It's another feature importance potential. But our learned binary mask is in orange. This is a brain neoplasm where you see blood pressure, heart rate, intracranial pressure, diastolic blood pressure, cerebral perfusion pressure are features that the RNN does not know the diagnosis of the patient. It only knows the physiology and what's recorded in the EMR. But it's able to pick out these features as important in its prediction. The LBM is able to. This is a patient with respiratory disease, ARDS. And again, the features that are most important are those that one might expect in a patient with severe pulmonary disease. So we're moving towards being able to interpret what features are important. We have multiple ongoing investigations in the ICU. I do want to mention that we have a data science program to train data scientists and pediatric critical care fellows together in data science projects. They do an internship with us, and the goal is to publish a paper, but we'd like them all to at least submit and present an abstract in data science and critical care. And we are continually taking VPICU data science interns. And finally, we've heard a lot this morning about get the data. We need to start sharing data. The VPICU sponsors a project, which is a cloud-based trusted research collaborative in pediatric critical care, has about 8 major children's hospitals all signed up and legally dotted, and we have our governance, and we have our data model, and we have our data structure in the cloud, and we are starting to receive data that all the institutions will share. And our goal here is to have over 100,000 critically ill episodes for all of us to benefit from in data science. And thank you very much. I'll stop because I think I might have talked too long.
Well, thank you, Randall. That was an excellent talk. That internship is a fantastic idea. That's a really great idea. Just in the interest of time, we'll keep moving along. Next, I'd like to introduce Dr. Suresh. He is the Chief Information Officer and Chief Medical Information Officer at UPMC Children's Hospital of Pittsburgh. And I will let you take it away.
Thank you. Thanks, Hamilton, and thanks everyone. And to AIMed for this opportunity. Just give me a second while I share my screen. Great. You should be able to see my slides. Quick disclaimer, I'm not an expert in AI or ML or deep learning or any of the related technologies, but as a clinician and as an administrator and as an executive sponsor for a lot of these projects, I'm able to provide input and hopefully add some value. I'll quickly go over 3 use cases that we have. Most of these are early stages at UPMC Children's Hospital of Pittsburgh. The first one is the application of sensors and machine learning in the evaluation of hyperactivity in children. And thanks to my colleagues, Oliver Lindheim from the Department of Psychiatry and Mayank Goel, who's with the Human Computer Interaction Institute at Carnegie Mellon. So they are the guys who own this. I'm just the clinical consultant. A quick background, hyperactivity is a core symptom of attention deficit hyperactivity disorder. There are actually no objective measures which are in wide use in clinical settings. The current standard measurement for hyperactivity still consists of parent and teacher questionnaires. And as you can imagine, this subjectivity leads to both over and under diagnosis and hence over and under medication. So the objectives for our project was, number 1, development of Lemur DX, which is a wearable smartwatch application that uses state-of-the-art sensor technology to measure the hyperactivity part of ADHD. To test the prototype for variability in motion between children who have a diagnosis of ADHD versus those who not. And if successful, this innovative ML-based approach can complement, not necessarily replace, the current diagnostic tool. So phase 1 was prototype development. Our custom application records the accelerometer and gyroscope data from a pretty much an off-the-shelf LG Sport smartwatch. The data is recorded locally onto the watch and then transferred to a secure server. And the clinical goal is to differentiate children with ADHD hyperactive presentation or ADHD combined presentation from children who just have typical levels of activity. Phase 2 was the feasibility trial. So we had 20 participants. It's up actually a little bit more now, but I'll just show the data for the first 20. All of them were boys with a mean age of just under 8 years. They were asked to wear the watch for a day, 24-hour period, and go through their usual routine. The parents maintained a diary of their child's activity, which were logged at 30-minute blocks from 6 a.m. to midnight into 4 activity classifications. So these were the 4 categories. Number 1, sleeping, either nap or longer sleep. sitting or quiet activity, which could be watching TV, reading a book, using a computer, etc. Number 3, just regular household activities, walking, cleaning a room. And number 4 would be exercise, playing a sport, or just running in the playground. So this was the descriptive data from the feasibility trial. What you see on the left side of the screen, the 10 patients with the ADHD and the 10 controls. So you can see fairly marked differences in the age, the hyperactive score, and the score for the various activities. And the descriptive data was pulled from activity diaries, were completed and submitted by parents at the end of the day that the child wore the watch. So as you can see, this was very much a pilot, but we wanted to do this phase first. And the hyperactive score, what you see in the table, is a standard validated score called the Vanderbilt Hyperactivity Subscale, which has been there for a long time. So moving on to results, the pilot data confirmed the importance of contextualizing motion data for assessment purposes. So children with ADHD and children without ADHD look most different in contexts where they were expected to sit quietly. So if you look at this part here, you have the time on the x-axis and frequency on the y-axis. If you look at the reading part of the block on the right side of this image, so there is a pretty obvious difference that even I can figure out. But on the left side of this image, while they were playing, the images, the tracings were more similar when exercising or while physically active. So we summarized that the observations are significant, given that the current state is that there are no widely used objective measure of hyperactivity to assist in the diagnosis of ADHD. And there is a great need for those of us who are clinicians and pediatricians and behavioral therapists know there's a great need in various settings of care, not only in pediatric primary care practices, but in children's hospitals, behavioral health clinics, et cetera, for such a complementary tool. In the feasibility trial, we use the activity diaries to track context. Next steps, we plan to develop a more multi-level classification approach, classify the various activity, you contextualize the level of motion, and evaluate the activity level based on that context, using the same accelerometer, gyroscope, and location data. Just a graphic representation of what I just said. We're planning to classify the activities into at least 6: running, walking, studying, writing, eating, watching TV, etc. And you can see how the machine learning part of it works using some tracers. Future directions, hopefully commercial product development. With feedback from focus groups, we definitely need to enroll a lot more patients before we get to that, and iteratively refine the algorithm as we go forward. I want to acknowledge some funding. This was a grant from the National Institute of Mental Health. The funding period is over, and now we are working on the phase 3, which hopefully would be a funded STTR grant, an R42. Switching on to use case number 2, all of us have heard this quote from Peter Drucker: if you can't measure it, you can manage it. Just going one step further, if you cannot automate the measurement of it, it's difficult to improve it. So use case number 2 is what we have as CHP view, which is virtual intelligent early warning, a sign of clinical deterioration, not very different than what Randall just talked about. And my selling point to doctors and nurses is to say that as pediatricians and even as clinicians, how do we generally take care of patients in the acute care units, to some extent in the ICUs too. We look at the patient, then we look at the monitor, then we look at the EMR, and try to gather pieces of data and try to figure out, is this patient sick? Does he or she need to go to the ICU, etc. But I can only process 5-10 pieces of information at one time. Most humans, all of us, we can do more than that. But what if you have access to 25, 30, 40 variables, clinical assessment, labs, and maybe even some nursing notes, which could be textual and unstructured. And if you can do that for all the patients in our hospital all the time, every X minutes, 5, 15, 20 minutes, etc. The human mind cannot do that, but a machine can. So that was a premise for us to get to this. Thanks to my colleagues, Chris Horvath, who is an attending physician and also an informaticist in our PED CCM division, our in-house data scientist, and Gabriella, who directs healthcare analytics. So this is the schema for what we are doing with the View project. What you see on the left side, pretty straightforward EHR, connecting to Oracle databases, and then to our servers, and we use Click as the visualization dashboard. And R for ETL and an R-Shiny application so that it is viewable at the bedside in the patient's chart. So just a screenshot of our Cerner EMR. On the left side of the screen, you see our menu or table of contents, and you see Acuity Index right there. You click on it. There is a graphic representation of the score, which is essentially a risk score for clinical deterioration in the next 6 hours. And we have some very key endpoints: transfer to the ICU, condition A, which is our in-hospital term for arrest, or condition C for critical condition, need for mechanical ventilation or pressor support, blood transfusions, etc. And we're able to track this in near real time. I won't go into more of the details. Randall explained it better. We have started piloting it in a couple of acute care units. I think the difference from what Randall mentioned is the focus here is in acute care units, not so much in intensive care where you have one-on-one nursing and more support even for a critically ill patient. But how do we prevent or predict a transfer to the ICU for the child? And efficiently managing acute care beds and ICU beds is pretty critical to any hospital's financial health. The rough financial value we derived was that if we reduce the mean length of stay overall for the year in acute care units by 1 hour for every patient, that leads to a net cost savings of about $400,000 annually. So a couple of papers we have published, again, theoretical a little bit because it's still pilot data at this point. This was in Pediatric Critical Care Medicine. And we wanted to do some subscores. What I just said may not work for the newborn babies, may not work for patients with single ventricles. So we have to refine that and not have a single algorithm with 43 variables. So this was specifically for our cardiac ICU patients. Switching gears again, before I go to case 3, I like this quote, so I just want to say it. In God we trust. All others must bring data. This was by Professor Deming. The last one, using AI to augment emergency department throughput measures and improve patient experience. This is very early stages. We haven't inked the contract yet, so I'm not able to share the name of the startup. It's through UPMC Enterprises, which is our commercialization and entrepreneurial arm. And the way this works, I don't have slides for this, is the patient checks into our emergency department. And once we get their mobile phone number, which 99% of families are willing to share these days, they get a text which sort of connects them to their version of the child's EMR, so to speak. There is no app to download. So while they are waiting in the emergency department, if I order a CBC or a chest X-ray or a consultant to come see the patient, that pulls in our ADT feeds and AI and explains to the patient that their wait time after they've been seen to get a particular test result back, to get the CT scan result back, etc., will be X minutes based on the time of the day of the week, and tens of thousands of patient data who have had similar tests ordered in the past. And we're fortunate that I work in the busiest ED in the city. We get about 80 to 82,000 patient encounters annually. So we're able to use all that data and timestamps and throughput measures so that we can provide these data to our patients and families on their mobile devices at point of care in real time. Just a couple of slides to finish off. When we do these projects, putting on my administrator hat, it is important to get clinician engagement right up front. So I love showing this slide, which is from a paper by Professor Friedman. I should probably show the right side of the slide first. What informatics is not, as you can see, it's the man versus machine or a person versus machine debate. What you see on the left side of the slide is a fundamental theorem where person plus machine is superior to just the person himself or herself. And my last slide is to talk about value equation in healthcare. This is important as we do these projects. And if we have funding from a grant to do a pilot, that's great. But how do we sustain it? How do we expand the impact of it to multiple patients, multiple providers, multiple hospitals and health systems? We have to look at a value equation. And very simply put, value equals quality over cost. And I think every physician, every data scientist, every administrator needs to know this equation. And then you can sort of expand the equation. What is quality? Outcomes per safety plus surveys. And in most cases, you can get some numerical data for these. So you can actually plug in numbers and solve this equation before getting onto a project or deciding, should I sustain this project or not? And I will stop there, and I'm glad to take any questions and participate in the panel discussion. My email is there, my Twitter feed is there, and happy to receive feedback. Thank you.
Well, thank you so much, Suresh. That's an excellent talk. Extremely interesting, and I actually really like that last slide because it seems there are no shortage of ideas on projects, but picking the right one to invest relatively scarce resources as far as data scientists, especially an institution like mine, is tricky. I'm sure there's lots of questions from the chat, but we're going to move on with the last talk, and then we'll address all those questions during the chat session. So now we're going to hear from Howard Lay. He is the senior data scientist at Children's Hospital of Orange County, and he is going to talk about agile data science for healthcare. Take it away, Howard.
Okay, thank you, everyone. Just please share my slides here. Let's see, I have to, just 1 second. Okay. Sorry, let me share my background. Okay, screen 2. All right. Okay. Okay, can you guys all see?
Yes.
Okay. Sorry about that. Hi, everyone. Yeah, so my name is Howard. Thank you for the introduction. And so this talk is, so it's slightly tangential to deep learning, but I'll mention deep learning towards the end and just one of the projects that we're working on. But it's mainly about promoting agile data science and how that can be really relevant to healthcare. And I also work with Dr. Anthony Chang, and he had a lot of input to the ideas in this talk as well. So just a couple of current issues that motivated this work. So first is COVID-19, which has brought greater minute-to-minute urgency of patient treatment. Although I did read about a vaccine that Pfizer sent out recently, so maybe this work will not be as relevant given the presence of that vaccine, but we'll see. But anyhow, I think a more broadly applicable concern is that we want to be able to deploy predictive models in clinical environments that are useful, and also do so in short timeframes. Right? So how can we do it more accurate and faster? And I think one of the issues in data science is that a lot of model development happens using what's called the waterfall methodology, at least when I worked in the past. And what happens with this waterfall is that, the data scientist or the work proceeds in a step-by-step process. So you start with the requirements, the design, implementation, verification, and maintenance. And this methodology, is traditionally used for software development. And with this methodology, right, we can apply it to data science as well, right? So with data science, you have data collection, data preprocessing, augmentation, model selection, right? Model tuning, selecting the right hyperparameters, also model training, and validation and evaluation. So you have this whole sequence of steps, and when one step in the overall process is blocked, right, then the whole process cannot continue. So then the model doesn't get deployed, or the data science needs to go back and either get more data or try to tune the models better. So the data scientists, in other words, would tend to work in a black box, focusing on these steps without a lot of input from clinicians or other domain experts. And this diagram kind of illustrates what I was talking about, right? So you have the domain experts in the beginning who would define the final requirements of the project. And then after that, the data scientist would kind of work on its own, right? And just to collect data, develop the models, check whether the model meets the requirements, and go back again, right, in order to improve the model. And then once the model meets the requirements on the data sets that the data scientist is testing on, then the model gets deployed into a real world setting where it gets evaluated by domain experts again. And the downside to this is that, first of all, domain experts don't have much interaction with data scientists. So domain experts such as clinicians may not really know what's going on, right, as the model is being developed, as the problem is being worked on. And then finally, even when the model does get deployed, in the final step, it may not achieve the right kind of accuracy or the reliability that's needed in a clinical environment. So that's the downside to using this waterfall methodology, this sequence of steps where in the end, right, you may not even get what you want and you just wasted a bunch of time in trying to develop it. And furthermore, I think in healthcare, it's even more challenging, right, when we're trying to apply data science to analyze complex problems and complex data, because the data is complex. So the data scientist needs even more time to pre-process the data to get the right data. And the clinical questions need to be well defined. And I think in my experience working at Chalk, sometimes we may not know the right clinical questions in the beginning, right? So we may have to try something and then refine the questions and then try something else. And we go through this iterative process until we get the right questions. And of course, the models must be reliable in a clinical setting, which means that after all the data science work is finished, right, we have to make sure that the model can be useful, for helping patients in, let's say, the ICU. So given these challenges, what we want to propose is this is not necessarily a new framework. I think it's conceivable that many of you guys or many people have been using this framework already, but we're just trying to give a formal name to it. It's called Scrumban, which is an agile data science framework. And Scrumban here is a combination of two software development frameworks called Scrum and Kanban. And both of these frameworks are meant for high velocity development of and deployment of production quality software, right? So there's sort of that with these frameworks, there's regular feedback that you get from domain experts, and then there's more of, I guess, a sense of urgency for the software to be deployed within a certain amount of time. So this is what the Scrum framework looks like. And I think for me, I had experience working on a agile software development team in the past as a data scientist. So I got to work within this Scrum cycle where, and the whole idea here is that you have a team of people, and this team would define requirements, right, every, let's say, couple of weeks. And in my case, it was every 2 weeks. And then within those 2 weeks, right, the team would go on a sprint and try to do as much as it can to push out the the software to meet the final requirements of that were discussed in the beginning. And then after the sprint is finished, there is a retrospective where people evaluate, okay, what were the tasks that we were able to meet, what were the goals that we couldn't meet, and what are some things that we can improve, and what are some things that we need to do for the next sprint, so next 2 weeks. And this is how basically the modern software development progresses, right, at companies out there. So I got a chance to experience working on this kind of a team. And but as a data scientist, right, I had to try to make sure that my data science models can be deployed and developed within a several week time frame, along with the rest of the team. So Scrum is one of the components of Scrumban, and the other is Kanban. And this one, and I'm sure many of you have already heard about this too, but it's where we can break down complex problems into subtasks. And then each subtask can be written down on a card on a board like this. And this is called a Kanban board. And, and as a task is finished, it would progress from being a backlog to being in progress, to being review, to being complete. And then you can have certain tasks that are blocked, which means that the task cannot continue unless some other thing gets resolved. Of course, you can have different kinds of Kanban boards, right? You can have different categories across the top, depending on which kind of development you want to do. So Scrumban, in other words, is a combination of Scrum and Kanban. So within each Scrum sprint, each team would have a Kanban board where they would break down the set of goals and requirements that were discussed before each Scrum sprint, and then track the progress of each of those little items within each sprint. And after the sprint is over, the team can evaluate and see how many of these items were finished and how many needed to be further refined or worked on the next sprint. So when we apply this approach to, healthcare or any other, I think, kind of complex problem, we get the diagram that's shown on the bottom right. So instead of the figure on the top left, where we have the data scientists working in isolation for a long period of time, we can have a situation where we have multiple rounds of collaboration between physicians and data scientists. And based on my experience so far with working at Chalk, right? And that has been the case where I would work with Dr. Anthony Chang, and we would define clinical problems, and then look at the questions and figure out where to get the data, even talk about what models we want to develop, and then go back and refine the models or the data or whatever else we needed. So we going through these multiple cycles. This is a much more effective way, right, to developing models, because it brings a domain expert involved into the process itself. And furthermore, I think this is faster, because the whole idea with Scrumban is to increase the velocity by which we can push the models out, right? So that we don't waste a lot of effort, that each effort that the data scientist engages in is aligned to a clinical goal or clinical outcome, right? So that none of it gets wasted, hopefully. Just like a quick example of, how this can be applied would be, suppose your clinical question is to detect COVID-19 using chest X-ray images, right? And then the next step would be to acquire the data needed to build a predictive model. And then you would develop the model, right, that's hopefully aligned with the clinical questions that have been defined. And then the goal here is to quickly get a model out that achieves minimal viable performance. And that's called a minimal viable model, MVM. And I think in software development, there's a concept called the minimal viable product, right, which is where it's the minimal kind of expected product that a company needs to produce, in order to meet the demands of customers. But so in data science, we can have a parallel concept called the MVM, minimal viable model, that could be minimally acceptable, right, in a certain environment. And that model can be quickly deployed. And then at that point, right, the data scientists would round with physicians to go back and repeat previous steps as needed, evaluate how the model performs. And so I think the key really here is to try to quickly develop a model and test it right away, right? Instead of letting the model sit, right, in the pipeline for a long time, waiting to be deployed later on. So for in my experience, right, we were able to use sort of that approach to arrive at a CNN that does a problem of detecting whether there's ductus arteriosus or not in an echocardiogram image, right? And so for this, we have to collaborate with multiple physicians to get the right data, and a lot of just communication, a lot of input from different people. In fact, the algorithm development itself was really simple, right? To train the convolutional neural network, right? And this network is already prepackaged available in the Keras Python framework. But of course, the hard part is to do the collaboration with clinicians and data scientists to get the right data and to evaluate to see whether this model is doing well or not. And so far we've been able to get it's not a lot of data we got so far, but we had 0 right a few months ago. So we have been making some progress. We have 96 training validation images and 20 test images, and so far the model has produced very encouraging results. In fact, it was able to perfectly detect the 20 test images, although there needs to be a lot more data to confirm that things are working the way it's supposed to work. But yeah, so and because we need more data, that requires more collaboration, right? It requires for us to continue to do this agile mindset and this agile approach to get more data that's needed for this model. So just to summarize, I think the key takeaway to this is that we want to have an agile mindset, and I think agile mindset means we want to be able to put models in clinical environments right away, right? We don't want to spend a lot of time trying to refine the model, to get that last 20% improvement accuracy, which could take 80% of the time, right? We don't want that. We want to get a model that performs 80%, deploy it, and then refine. So that's an agile mindset. And to do that, right, it requires more, of course, physician and data science partnership. I think right now, there are a lot of tools out there, right, that could facilitate these partnerships, right? We have a lot of cloud frameworks where you can have multiple parties looking at the results online, publicly available data sets like Mimic, all these things that are that allow collaboration. And but right now it's just getting the two sides involved and willing to collaborate together. So so that's the end of my talk. So feel free to ask me any questions. Thank you.
Thank you so much for that, Howard. It's a great talk, very enlightening. I think it's a really important point as we move forward, trying to get some clinical tools on the ground as far as the clinical workflows. With that, we'll open it up to the panel discussion. I think we'll start out with a question that we had in the chat section for Randall. The question was, are these algorithm prediction models unique to the individual PICU or transferable?
Good question. I think that our goal has been to demonstrate the feasibility of these methods. And I do absolutely think the methods are transferable. Now, most of our conclusions are based on 20,000 patients or so from one children's hospital. One reason to build the collaborative network is to expand the generalizability of these predictions on patients from around the country. But I would not say, give our model, pass our code on to another hospital and say, run this on your patients. Definitions vary, the type of data varies, the data models vary. Just to talk about applying an RNN is easy. However, making the data suitable and understandable and accessible is essential, and that varies from place to place. I'm glad about the CARES project, but I'm afraid that when you've met one EMR, you've met one EMR. They're all structured differently. The data is all different. The definitions are different. What people call even things as simple as blood pressure. It's going to be difficult. So just picking up a model and applying it to another hospital's data. Obviously, we develop our models. We split all of our data and develop our models and then apply it to a holdout test set once to see how well it's performing. But I think that really the reality of the work we've done is the models work. the methodology works, but it has to be, at least for now, individually developed. Although, as you did see, we did produce a little app, which we're going to put online for people to use. But the app is requires entering data that is well defined in the app to get the right answer.
Yeah, it's an interesting point. I think generalizability is going to be a very important hurdle to a certain degree in getting a lot of these things started. A follow-up question to that I'd be interested in your opinion, Suresh, is, UPMC Enterprises and your institution is one, amongst others, it seems as though given quite a bit of forethought to not only development of these tools on the research side, but how to transition those into something that's generalizable as well as potentially even commercial. What have been your institutions and your group's thoughts on how to get over this hurdle?
Yeah, great question, Hamilton. And there are other examples across the country. And I think most children's hospitals, we are fortunate that, there's a university affiliation, and in places like, Pittsburgh and in other large cities, you have the at least an interest, if not active collaboration from industry. We have, Carnegie Mellon here, Google here. So at least you get the right infrastructure to think about, I have this product which helps thousands of patients in my hospital and hundreds of doctors in my hospital. How do I take it, to a region or nationally? And in addition to the barriers that Randall just mentioned, which are spot on, plug and play is so overrated, but you need that kind of collaboration from academia, from industry, from our hospital system itself. And having an enterprise, UPMC Enterprises, that's what we call it here, having that kind of an infrastructure, an innovation institute, somebody with business development background, things like that, which most of us, clinicians or informaticists may not have. I think it's critical. Otherwise, you have a lot of very good siloed projects. We could have done that for lesser effort if there was a plan to scale it up regionally or nationally.
Yeah, that's an excellent response. And I think Randall also answered that question with collaboratives too. I think that once you have that ability, then it will certainly help the problem. Couple more questions here. We'll see how many we can get to in the time remaining. A question for Howard. Howard, if you wouldn't mind joining us again by video. What is your take on the small number of training data used for assessment of PDA? What were some of the challenges you faced, since this is a small number to train on, which is of course something that happens an awful lot in pediatrics?
Yeah, I mean, I think there was some overtraining given the small number. Although the technique I used was transfer learning. So the CNN that was used, it was already trained on ImageNet. So the parameters were fairly nicely tuned already. However, yeah, we definitely need more data. So that's what we're trying to work on. So, but I guess what I showed was sort of like a demo of what was possible, which we hope to do better on in the future.
Yeah, and transfer learning is a great solution for small data, yeah, I think it's a challenge that's not going to go anywhere. So we need to find good solutions. One more question, see if we can sneak in here. Another one for you, Randall. Says Dr. Wetzel mentioned some neural nets that don't need feature extraction. How do patterns in the data, e.g. change in heart rate, feed into the models? We'd start there, and then there's some follow-up questions.
Good question. Feature selection. I'm going to go out on the limb just so everybody remembers this, is no longer necessary. Feature selection was from the old days when we didn't have GPUs. We only had little slow CPUs. There is information in all of the data that we have available to us. And to cast out some data because it doesn't fit an old-fashioned model of a multiple logistic regression analysis that can't cope with more than 10 or 15 or 20 or 100 variables. the RNNs and new GPUs can handle 1,000 variables at once. And I did demonstrate that feature selection to speed them up or to improve their performance wasn't necessary. In fact, we threw tons of junk into our data vectors and did not degrade the performance. We tried. To us, that's what the whole need for feature selection to improve performance or speed is. Just forget about it. However, one does want to have feature attribution. I would like to know why what the recurrent neural network considered important in coming to its prediction or conclusion. And so trying to figure out the relative feature contribution to the predictions is important. And that's a process not unlike feature selection, but it's not, I try and avoid the term because that always seems to imply old-fashioned machine learning with, I gotta get my PCA analysis done before in machine learning.
Right.
So that was the point of that demonstration. And yes, the RNNs are looking for changes over time. The recurrence of the network allows you to compare previous data and information gleaned from that data to the next step with new data when new data becomes available. And you can figure out, or you can look, let's say at the gradients. If you backpropagate error backwards, you can look at the gradients, how the output changes for individual inputs. It's not easy.
Yeah,
but
we're getting the red light.
The information is there.
Excellent. We had so many questions come in at the last part there, but unfortunately I've gotten the word from Alexis that we need to move on. And it's, I guess, a wonderful thing to know that feature selection is becoming relatively unimportant. They still teach it in classic data science because I'm actually taking a course on it right now.
So. Well, it's probably important to think about that because we still be able to, dare I say, interpret these models.
Yeah. All right, great. Well, with that, Alexis, would you like to take back over?
I can do the honor. So thank you, Hamilton, and thank you, speakers, for a wonderful journey into machine and deep learning and show what's possible. I'm so proud that these are all pediatric practitioners. So thank you very much. So, so we talked about data at great length this morning, just talked about machine and deep learning. Now we have to face another reality. I'm so lucky to have Matthew Diamond here from the FDA to give us the regulatory perspective. So Matthew, welcome. So
Thank you very much. Yes, thanks. Can you hear me? Anthony, are you? Perfect. And let me just try to bring up and share my slides. Just a second. Just one moment. Okay, are you able to see the slide I have here? Perfect. Well, Anthony, it is a pleasure to be here, and it's a great program. As you mentioned, I'm here to share a little bit of a regulatory perspective from the Center for Devices and Radiological Health, where we frequently review artificial intelligence and machine learning-based devices across really a breadth of medical disciplines. And the first thing I want to do is to zoom out a little bit, and I'm in the Division of Digital Health, where we just developed a Digital Health Center of Excellence, and I want to talk a little bit about digital health more broadly as a field. Just a second. There we go. So, we want to recognize that there is a digitization across a continuum of healthcare, from on the left, just healthy living, and general wellness, prevention, diagnosis, treatment in all these areas. The use of digital data, the ability to collect data and deliver treatments in a home environment, in a work environment, and to bring the practice of medicine outside of a traditional clinic is really having a significant impact. And in the context of a pandemic, it really becomes a necessity. Again, we think of digital health very broadly and recognize that it has many applications. Not only are there medical products that are based on digital health technologies, but digital health technology are also used to create products. They're used to study products. And sometimes they're used in combination with drugs and biologics. It's important to put the work that we do today in CDRH in perspective of the last 40 years of work, and to understand that the regulations that were created to oversee medical devices were created in a different medical device world. This traditional medical device world, pictured here on the left, with a product development timeline that was much slower than what we're seeing for medical software. We go from months to years to now, developers wanting to put out updates to their apps on a weekly or monthly basis. We have a great availability and potential for post-market data. It's not like a hardware device that you put out into the world and don't hear from it again. A connected device, software device is really a relationship between the developer and the user. And the decreased barriers, and I think there's been some discussion of, what is the barrier about of going from developing an idea, an algorithm, and then actually implementing that into a clinical setting. Although there still are barriers, they are significantly less than for a traditional device that would require, manufacturing of hardware. And because of that, we are seeing exponential growth in the number of submissions to the agency, and in particular to our center. And I want to take a moment to define what we call software as a medical device, which we see as dominating this world on the right. And you don't have to go into all the details of this diagram, but I wanted to at least mention that software as a medical device, or what we call just SAMD, is what you might think of as standalone software. It's software that performs a medical purpose without being part of a hardware device. And it takes an input, uses an algorithm, which could be AI ML based, and delivers an output that's used as part of clinical care. And I want to give you some concrete examples. And today we're talking about artificial intelligence-based products of some AI ML-based SAMD that we've cleared at the center recently. And again, this is across medical fields. At the top, we see an ophthalmic and metabolic application for a product created, IDXDR, that essentially screens patients for certain types of diabetic retinopathy and will direct those patients to a specialist for care. And this is an example of a product that essentially will make a medical decision for that referral. Many artificial intelligence-based medical products would fall into the category of more assistive devices. An example of that is on the bottom, and this was a recent authorization of the Caption Health product, which allows a healthcare practitioner who is not specially trained in the acquisition of echocardiographic images it basically guides them as they take cardiac echoes, and allows them, essentially to those patients to have access to that technology. Again, especially important at a time when folks are restricted in where they can go. And it's a whole class of products that will allow technology like ultrasound to be performed in settings where it may not otherwise have been available. And so I think this group probably doesn't need convincing on the opportunity of artificial intelligence in medical devices. As I mentioned, there will be no field of medicine that is untouched, and its applications include better diagnosis, better treatments, and overall personalized care. And one of the strengths of these products is their ability to learn from the wealth of real-world data, as I'm sure you appreciate, and have the potential to improve their performance over time. Now, there are unique challenges and considerations, the need for high-quality data sets, the challenges of some black box approaches that are more opaque than the technology we're used to dealing with, and the presence of bias. These products are created using historical data sets and are vulnerable to the bias present in those data. So part of the work that we do at the Center for Devices is to develop a new regulatory framework, a new regulatory paradigm that is better adapted to these software-based products, including artificial intelligence, that allows manufacturers to improve their products while maintaining our assurance of safety and effectiveness, and allow patients access to these products as soon as they are safely available. And to this end, last year, we published a proposed regulatory framework paper describing a total product lifecycle approach to the regulation of artificial intelligence and machine learning-based products. And we just last month announced that we will be issuing in 2021 guidance document that builds on this discussion paper to help sponsors and the FDA develop and review artificial intelligence-based products. And I'll tell you a little bit more about that in a moment. I wanted to just pause for a second to acknowledge that when folks describe artificial intelligence products, they exist on a spectrum. And there are some in this presentation, what I'm focusing on is whether the algorithm in the product is locked. And in that case, discrete updates would be made. This is on the left. And on the right, products that would continuously adapt to new data. So the products that we've cleared at the center so far are of the type that are on the left part of this spectrum. So they are trained, the algorithms are created using machine learning approaches. But some of the more exciting applications and some of the products that will require additional work to develop a regulatory framework for are these products on the right that adapt even more frequently, and when these adaptations are performed by the actual software system itself. And I'm going to show a figure from that discussion paper, which depicts an AI/ML workflow. And you see in this shaded oval or rectagonal region at the top, a development environment where data is used to train a model. And then these two arrows pointing a green and white toward the bottom of the slide show the deployment of that model where new data is inputted, and the output of that data is essentially the result that's used in the clinical setting. What we described in the discussion paper is a multi-pronged approach for oversight of these technologies, starting with number one, an emphasis on the development environment itself, and what we call good machine learning practices, which would be analogous to good manufacturing practices and other good practices. It's important that the data that is used to train the model is dealt with appropriately, and these are meant to incorporate standards and best practices, in data science and software development. points 2 and 3 here in this figure are intended to represent the review of the product, where number 2 is a pre-market review, very much like we have today at the FDA. Company will submit a description of their product, its intended use, and the evidence that shows it's appropriate for marketing. And then what we've added here is number 3, a description of how the company intends for the product to change over time, leveraging the unique characteristics of AI/ML technologies. Lastly, we see is depicted number 4, especially if a product may be modified over time, it becomes even more important to monitor its performance. And that is the number 4 in the total product lifecycle approach. And I'll go just into a little bit more detail on 2 of these aspects. And starting with good machine learning practices, as I mentioned it earlier, there are actually numerous standards efforts that some of you may be a part of, looking at various aspects of artificial intelligence, some specifically for healthcare and others more generally for AI/ML. There are a number of international collaborations through the International Medical Device Regulators Forum. There is an AI World Team through Xavier University. There are numerous efforts, all trying to codify these GMLP practices. And at the agency, will certainly, not only will these raise the level of practice in the development of these products, but it will aid in the review of these products if a company can reference the fact that they are following these standard practices. And the other aspect that I just want to highlight is this idea of pre-specifying for a company to essentially tell us how they intend for a product to change over time. What is the purpose of additional training that the product will undergo with new data? And we're calling that a set of SAMD pre-specifications, or SPS. What are the changes that a company would like to perform? And the second area, which we call the Algorithm Change Protocol, or ACP. What are the methods, and a very detailed description of how the changes can be performed, and yet we can still have confidence that the device is safe and effective, essentially providing the guardrails that protect the functioning of the product over time. And just about my last slide here, this is taken from a SAMD document put out by that International Medical Device Regulators Forum that shows an iterative approach to product development for software. And we'll follow one circle around here, starting on the upper left, where you have what's called a SAMD definition statement, a statement of what does that product do, and what's the clinical circumstances in which it will be used, what types of conditions, what is the role that the software will play. Will it assist a healthcare provider? Will it perform a task that's normally done by a healthcare provider? And that definition statement is specific for a product and a version of that product. And then following around clockwise here at the top, once that product is released into the market, it's important again to gather real world data, monitor the product's functioning, and as we continue around on the right side of the slide, collect the data, analyze it, and build essentially new clinical evidence to advance potentially the claims of the product and improve its performance. And it's through this iterative cycle that we can both improve how our devices function and expand their use. And so our goals have been essentially to develop a regulatory framework that is more flexible, that is tailored for these technologies, and that encourages and facilitates this type of iterative development. So I think I'm going to finish there and pause and see if folks have any questions. But I also want to say you're welcome to write to me. We have an email address at the FDA, at the Digital Health Center of Excellence, is digitalhealth@fda.hhs.gov. This Thursday, we have a listening session, if you go on our website, that talks about the Center of Excellence, so feel free to tune in. and send us questions, and we love to hear more about your experiences, your challenges, and how we can be helpful. So thank you very much.
Thank you very much, Matthew. I'm a huge fan of how FDA has pivoted in the last couple of years in the software as a medical device domain. And I have a quick question. Has the FDA or you thought about using a more automated way of looking at the continuous learning model, i.e. actually use an algorithm to go against an algorithm? I'm only saying that because I remember Alan Turing's famous words, why have humans always be the only resource against machines? Why not have some machines be part of the process?
Yeah, absolutely. So we need to keep up ourselves and modernize. I think our leadership has joked about, artificial reviewers, artificial commissioner, and some decisions certainly need to be made by humans, but the volume of data that we are seeing and we will see, absolutely, we are investing in our own digital transformation and infrastructure to keep up with the pace of with what you all are doing in industry.
Great,
and
thank
academia.
you so much, Matthew. So I'm going to now hand over the moderator role to Dr. Randall Wetzel to cover an area that probably one of the most often asked questions I get, which is, how do I get started? You got me interested through meetings like this, and how do I get started on a personal journey or get going in my healthcare system? So Randall?
Hello, thank you, Anthony. And yes, getting started is often the difficult part. Are my slides up? Slide. Okay, sorry. And so motivation's important. One has to remember that medicine is inherently experimental. Even Hippocrates knew this, and he called on us to observe our patients and learn from the observation. Everyone. Over the years, we've done a gazillion experiments, but thrown the data away. And so motivation's important. Yes. And we need to capture all of that. In fact, failure to learn from our patients is unethical. Have a goal in mind, but get started. Have a question. I don't mean hypothesis-driven research, but know what you're trying to learn from whom and why. Have a well-defined question. Then get data, and you've heard a lot about that today. Curate the data. Pre-processing is a non-trivial step. Definitions, models, data aggregation, cleaning, removing false data, missing data, and imputation, which could be a whole symposium in itself, and target selection. Know your data, explore it, munge it, and understand it. Work with clinicians and data scientists together, and pick a machine learning methodology and understand it. Today, we have several experts with us to share their reflections on this before we get started asking questions. And the first one I would like to introduce, I think, I've lost her, is Rebecca Pope, Dr. Rebecca Pope, who is the data science and engineer at KPMG in the United Kingdom, and also at Great Ormond Street in the NHS Foundation Trust, who will share her perspective with us today. Dr. Pope.
Hi there. Hello, can you hear me okay?
Yes, indeed.
Wonderful. Thank you ever so much, and pleasure to be with you today. So I didn't know you were going to ask me my view, actually, which sounds slightly strange given that we're on a panel. But yeah, how about I give you kind of my penny's worth, which I think is often that there is a rush to to do the sexy thing called AI. And what we really mean by that, I think we're all on the same page, is machine learning and various forms of machine learning, as we saw earlier, including deep learning or natural language processing. And I think where I see both, so I'm very fortunate to be seconded 1 day a week at Great Ormond Street Hospital. But I also work at KPMG as a data scientist for non-healthcare clients, and where I see very interesting difficulties in the development and the deployment, irrespective of the great, I can't remember, was it can Scrum, or I can't remember the term, but irrespective of the non-waterfall approach to delivering data science, is actually we tend to not focus on the unsexy part of that equation, which is actually infrastructure, and the ability to have, to your point, Randall, are you capturing the data? If you are capturing the data, why are you capturing the data, and what data flows do you have across an organization, particularly around often a non-interoperable data estate? So I think a lot of what you need to do first is actually concentrate on that part, and then also around actually the cultural shift change and the data science skill sets, and that extremely important synergy between, so I'm a data scientist, but I'm a completely blunt tool unless I'm guided and working so I can code. That doesn't really matter, right? I'm not going to cause or be part of an impactful transformation that really helps patients unless I'm guided by clinicians, and unless we go through understanding the problem, iterating through the problem, working through the data science process and methodology together. Because otherwise I'll create an algorithm that I will say, oh, it has a fantastic uplift on an F1 score, and a clinician will just look at me and go, great, but that doesn't really help my my caseload or operational flow through the hospital. So my kind of moment is just to say, focus on that section, on the workforce and understanding and what you want to do in your infrastructure before catalyzing yourself to this magic bullet that often doesn't become very magical, and it becomes non-magical at a large cost very quickly, which is data science. So I'm going to pause there and hand back to you.
I certainly agree. The sexy part is running the algorithms and testing our performance. The tough part is data. And we have another panelist, Hamilton, who has been with us this morning. So Hamilton, your thoughts?
Well, thank you, Randall. Yeah, I think a number of those echo what Dr. Pope just said. That, it's interesting. I'm coming from a bit the opposite direction. So just to give a little bit of background to put this all in context, I really had no education as far as data science or real significant knowledge concerning machine learning or other AI techniques 4 or 5 years ago. And I admit that, as Dr. Pope mentioned, a lot of what initially attracted me to it after not all that long a period of time, I realized there was a significant amount of hype in that sexiness. But I think coming from the clinician's perspective and having that driving interest, it led me to push through all of that. And then I did get a look at the sort of underbelly of data science, which is really not very sexy and requires a significant amount of dedication to learning and understanding techniques that can at times even be a bit counterintuitive for clinicians that have spent a lot of time practicing medicine. But I think that realization that it was hype, but much of it was true potential, and that the way to really help things move forward in the clinical realm was educating clinicians. Because I really, I agree with Dr. Pope in my own limited experience in developing tools and trying to get them to the clinical side, that it really is incredibly important to have clinician input and guidance throughout the whole process. And I don't think that's anything new to most of the people participating in this conference. I think most of us would already have agreed with that. I also think it's, very important to think about, if you are just getting started from a clinician standpoint, what role you want to play, what you want to learn, because you certainly can expend a lot of energy and time chasing down different rabbit holes, et cetera, trying to educate yourself, because there is a dizzying amount available online for one to start educating themselves in this area, but it is of incredible varying quality and dizzying quantity. And so I think it is important to really give that as much thought as you can. What do I want to learn? Who do I want to learn it from? How am I going to use it? I really didn't think much about all of that, and I wish I would have. I probably would have saved myself a significant amount of time. But that ended up with me in a master's in data science that I'm enjoying an awful lot. And I think, as with some of us on the clinician side, even throughout our education, we, to a certain degree, find our path as we go. Not everybody starts medical school knowing they want to run a virtual PICU. We do define things to a point along that journey, but it is important to have a good starting point for that journey. So I think that's probably my best answer to the question of how to get started from the clinician side.
Thank you, Hamilton. I think we have a few more people with us, and I'd like to ask Addison Gerhardt, who is a clinical fellow at Boston Children's Hospital, who is perhaps closer to getting started than some of us are. Please share your perspective, Addison.
Thank you, Randall. Yes, I'm pretty junior in my interaction with AI. I started developing an interest when I was at Chalk as a resident with Dr. Chang. And he had enlisted my help to write a review paper on AI and cardiology. And to be honest, I had literally no idea what AI was, but I just wanted to interact with Dr. Chang and learn more from him because he's brilliant. And that sort of started my journey. And I was fascinated by kind of how removed we were in our medical school training with AI, as well as our residency. Like, I had no concept of AI in the medical field, the ethics of it, the potential to dramatically change our patients' outlook and the way we as clinicians view data. And it for a while, I was a little bit cynical because I was like, wow, there's so much data that I'm being forced as a resident to look at that I can barely comprehend. And like, why don't we just have AI? Like, it doesn't make sense to me. Like, we have this one size fits all approach, but we have such complex patients in pediatrics. We're borrowing data from very limited, with studies with very limited populations. And we're not as collaborative as we should be. So that kind of piqued my interest. And I was sort of the tail end of my residency. And then when I came to Boston Children's for cardiology, I started trying to find the community of AI, which was actually not as robust as I would have thought, given that MIT's nearby, and so forth. Since I've joined, there started to be Boston Children's AI and machine learning working group, but that's sort of in its infancy. So I started meeting with as many faculty members as I could, asking if they would kind of sponsor me in AI. And they were all like, oh, we have no experience in this, but we want to facilitate you learning more and you getting the project you want for your fellowship. So Dr. Powell, who's a cardiologist, who's one of the heads of imaging at Boston Children's, agreed to mentor me. And I'd been reading the literature on kind of on AI and cardiology, and I had an interest in echocardiography in particular. And I actually found out that there was someone at Brigham just down the street who was doing exactly what I wanted to do in adults. So I just cold called him and emailed him and said, hey, can I join you? And will you teach me kind of how you develop convolutional neural networks and how, and can we kind of borrow your project idea in adults for pediatrics? Because I think there's a lot of parallels and how this could be interesting. And it's been, like a lot of people have mentioned, a very iterative process of like learning to communicate and collaborate and speak the same language. Sometimes like we'll give, like right now I'm in the process of looking at echocardiograms in pediatrics and trying to do view classification modeling. And so I'm learning a ton in the process, and I'm not getting a formal education in AI, but it's just sort of this meeting and asking questions and being interested and being willing to help with the data processing and giving the clinical, my clinical acumens to try to move the project along. That's making the project work, and it's really fascinating and fun. So
well, that's terrific and a very optimistic perspective. Your grit and determination and curiosity found an AI working group where you thought none existed. I think that's good information for everybody who's considering getting started. Just roll your sleeves up and get going. And we wish you all the best. But now let's go over to an old friend of ours. Hello, May, who's at Georgia Tech and has been a participant in this meeting for a long time. Your perspective, May.
Okay, thank you, Randall. Thank you, Anthony, for inviting me. So I'm actually a data scientist. I started this in my college year back in Tsinghua University many years ago. But I would like to say how I got started in the medicine side. I always want to be a medical doctor when I was young. So when I was leaving industry, biolabs to go back to academic, I chose the biomedical engineer department of Georgia Tech and Emory. That's how I started working on medicine. So trying to address a few issues, Randall prepared us a few questions. I would like to share what are kind of obstacles I run into, how I get help, and then from that, how I see we can actually help everyone get started on AI in medicine. So the major obstacles I run into early years actually are really the access to data and also understanding what's the goal, what's the questions. So that's actually, I think, not only this is applicable to data science, it's probably applicable to clinicians. You want to figure out what you want to do. You want to be a user, or do you want to be a more beyond user, be part of the designer of the AI? So I think that's actually one thing is related to goal. And then the obstacle wise, this is what I discovered during the process. Finding the people who are in handling of the clinical, in the clinical setting, to me is the most critical part. That's actually related to the comments made early on about team. You learn the best from team if you don't want another degree in medicine. For me, right? For clinicians, you don't want another degree in computer science or data science. You probably work in team. That's the most efficient. So that's what I learned over the years related to how start in AI, which is finding the people who had a problem. For us as data science, go to the clinical setting, be in the clinic, learn the problem, and then address the data access, eventually also working with a physician to validate the result. And then for clinician, working with a data scientist, a student, resident, and industry professionals, largely is trying to understand behind that black box, what is the conceptually, what's there. So to me, that's the critical part, which is the goal, the team, and also the ideally is how to get started in this.
Thank you very much, May. Let me ask, I'm waiting for questions to show up from the audience, but while we're waiting, let me ask each of you, what was your biggest challenge in 5 seconds or less? What was the largest, most challenging thing you had to overcome to start doing clinical data science? Let's pick on Rebecca, since she got to start.
Thanks very much. I think the hardest thing, because I didn't come from a traditional physics background or coding background, I'm a neuroscientist by trade, was learning the mathematics behind the algorithms. Because I think it's one thing quite easily, you know, you go to GitHub, you download something, you pump some data through, ta-da, here's a model. But actually, do you really know what it's doing? And to the point around deployment, you really need to understand deeply statistics, linear and nonlinear algebra. And for me, that was a real challenge because that wasn't my background.
I like your statement about you really need to understand the model. And yes, that does mean at least getting an intuitive feel for the maths. We've heard the word black box several times. It isn't a black box. There are people who actually know how the box works and how to extract information out of the box. And I think we probably do ourselves a disservice by continuing to refer this as a black box. Clinicians shouldn't be encouraged to think it's an uninterpretable model that we can never understand. We can. May said the same sort of thing, you know what's going on in there. And if you don't, we need to find out. So Addison, I don't think you had any challenges. You just knocked them all down one by one. But what was the worst one?
I think the hardest one for me is time management, because I'm trying to be a fellow in cardiology as well as keep my foot in AI and stay up to date on the literature, as well as like learning the methods. So I think that's the challenge for me, is sort of time management. Yeah, and learning all the information.
You're doing a 5-year fellowship, right?
I'm trying to convince my PI at Brigham to hire me as like a clinical fellow in AI, but we'll see if it pans out.
Good idea. Hamilton.
I think probably the biggest challenge would be getting all the people in the right room at MUSC to move things forward and try and unite the powers of the relatively limited resources that we had between data science, informatics, et cetera. Yeah, that was 5 seconds. So
it's very important to bring those together. We have all seen, and maybe we've even practiced in our olden days, even before AI, that we do experiments or have ideas, and we walk into the statistician's office and say, just give me a significant p-value, and walk out, not understanding or learning. As with statisticians, it's best to sit down at the start of the project and work with them. Certainly true for data scientists. Just don't get your data together and go and say, could you just tell me what the clusters are here, and so I can figure out what's happening to my patients. Team. So let's see, how would you each advise clinicians who are wanting to become involved, who realize that this is the way to go, and there are some new tools that are the only way to answer a lot of the questions? What would your advice be? I'll go in reverse and put Hamilton on the spot this time.
Well, that's easy. I think that I think it's pretty undeniable that machine learning, AI, deep learning, et cetera, is going to have a significant impact on medicine. It's just a matter of time, effort, and how that's going to happen. I think my advice to them would be to learn to your level of motivation, because if you go beyond that, you'll lose your interest, and everybody's going to play a role at a different level.
Good advice. May, see all those young clinicians out there who no doubt have come and said, help me, help me.
Yeah. So I actually suggest, same as what Hamilton said, but I do suggest that if you're a clinician, the best way to learn is learn something you are expert on. So that's why share your data, and having people working with you on your data. That's one way to really learn. And then that's one thing. Second, I think also Hamilton mentioned early on, finding the right source. Right now, there are too many online material available. It could become big time waste if you go for low quality material to start with. So in that regard, I do want to mention about this review course Anthony organized. That's actually organized by the domain expert physicians with AI. That's become an easy path for a physician to get into the door of AI. And so that's my 2 recommendations.
I do think it's important for clinicians to start to understand, but it's also important for us when we publish that we realize that we're talking to clinicians, and we have to be able to clearly explain explicitly and in some detail what we do. and start raising the general AI IQ and get people more on board. Dr. Pope, you wandered into the clinical world from the science world. What advice do you have for us who never got out of medical school?
So disclaimer, I'm not a medic. I have a PhD. I have no clinical training whatsoever. I just code. So just putting that out there first of all. So just replay the question for me.
You've worked with a clinician you've worked with. What advice would you give them to make their journey a little smoother?
I think it was touched upon earlier, potentially by Hamilton, which is, and your role can be fluid, but what is it that you really want to do? Because I think there is this the potential expectation that you can be a data scientist, you can be a physician, you can be a domain expert. And I'm not saying you can't be those things, but for a lot of people, for the very reasons that Addison mentioned, is actually, what do you want to do? Do you want to change clinical care? And therefore, are you going to be the person that starts to have a hive mind and bring people to you and magnetize people to make that vision come true? Or do you want to be a data scientist and a clinician? And I think it's really difficult to know what that is, and I think that will change over time. But I think it's about that network, isn't it? And to Addison's point, you know, the reason I happen to volunteer at Great Ormond Street is because I harassed the CRIO to say, look, I really want to learn about this domain and understand why in banking I see AI deployment at scale. I'm not seeing it in the UK NHS. Why is that? And if you turn that on your head, you know, what is it you want to do as a clinician? And then start to put the people around you, because all ships kind of rise together. And I don't think don't put too much pressure on yourself to be this unicorn, because they really don't exist.
Well, thank you very much. I would ask Addison, but for time purposes, I'm not going to. And besides, I think it's unnecessary. Her example serves eloquently, probably more eloquent than us older folks have been in expressing what clinicians need to do to get on an AI. And I think I'm over to Anthony for closing remarks for today. Thank you, panels, for everything. Great working with you.
Thank you, Randall. And thank you to our panel for this discussion on the personal journey. And the key word there is personal, I think. So Randall probably remember life comes full circle. And I've been talking about a supercomputer that can help make decisions since the 1990s at one of the PCICS meetings. And I ended up paying a pretty high price to go back to school and get that domain knowledge. But I think, and you know, being out of place, of course, and I often tell my my team, going back to school and being with people a third to half my age who are much smarter than I was like being an average weekend athlete and now playing ice hockey against the Russians on the Olympic rink. You know, just totally out of place. But what I learned was tremendously insightful for me, and just to be not just a better, just not just to have a career in understanding this, but becoming a better doctor and think differently as a doctor. I think that every clinician should benefit from, and just get away from mostly system one thinking and start thinking system two, like our data scientist colleagues, I think is very important. And I think in regards to all of this, I sort of draw the analogy to music. You know, you can be sitting in the concert hall and just understanding, enjoying the music. I'm a violinist. You can play the music or you can compose music. I think it doesn't really matter, as I think the last session is demonstrating. I think just get into the concert hall and do something, because medicine is in such dire need for a major transformation. And I think we're all here at an AI in Pediatrics meeting. It's one of the first, actually, that focuses on pediatrics, and we particularly need it in pediatrics. And I'm very inspired by all of you here to want to learn about this. And I know our discussion today may seem a little bit daunting, or it's easy to have some pessimism from all the data issues and all the IT issues. But if it's not for AI or something else to transform medicine, then what will transform it for the future? So I have some cautious optimism that a decade or 2 decades from now, we'll be looking back and say, what an amazing transformation that has happened, because we had to change data, we had to change IT infrastructure in healthcare to get exactly what we want, which is hopefully someday the personalized medicine that we all want for our children and our pediatric patients. So with that, I want to thank everybody again for an amazing 4 or 5 hours. We'll have the second day tomorrow. So we'll see you tomorrow.